Yes, so I would like to start by really thanking a lot the organizers, the whole organization of this incredibly well organized conference that give us the opportunity to talk again face to face. I never had the pleasure actually to co-write a paper with Lee, but I had the incredible experience of arriving as a young postdoc from France in the East Coast at the right time with the right people. And it was for me just incredible amount of information that I learned at the time. It was in the early 90s, some time ago. And it was a time where most of the notions that are now widely accepted were starting to emerge, were hotly debated, and really that moment shaped completely my career. And of course, like everybody, I'm very indebted to Lee's ideas. I have my own copy of the Bible, but I cannot show it to you because actually just before coming, I gave it to a new PhD student with the instruction to read a few chapters before I come back. So no, I won't solve all these questions. It's not even a broad review of the subject. It's more a list of open questions that kind of still bother me on this topic. And there are excellent recent reviews on the topic, especially by Tom on the in PP. So I don't know if it's maybe I missed the numbers PP5. So yes, this talk I will concentrate here on the origin of jet and outflows. Focusing on observations of the very inner regions of these outflow phenomena. And I just want to remind you that we now know that jets and outflows persist even through the planet formation stage. And I show here two striking examples of two of the striking examples of disks with rings that we know, a Tittori star and a Higby star, and both are very well known for also driving prominent atomic jets. So the jet launching mechanism is robust and coexistent with planet formation. So yes, we have very stringent constraints on the origin of the jets, and the current direct constraints on the base of the jets place them at less than a few AU from the central star. What I want to remark here is that the jets are very rapidly collimated on scales less than 20, 30 AU from the driving source, but we do expect that jets at the base have a larger opening angle. So jets should start as conical winds, and that's something we will come back to later. This property, this collimation property, and other ones, which I won't list here, and I refer to the very excellent review by C.V. Cabri in 2007 for all the arguments in favor of magnetic jet launching, but in particular the collimation favors a magnetic launching mechanism, and the principle behind magnetocentrifugal ejection is that you have a large-scale magnetic field anchored on a rotating object, creating a B phi component, which itself produces self-collimation. And there's been a wealth of theoretical developments in the field of jet launching models. So in the very inner regions of the jets of the star disk system, we have to take into account the fact that the central star, Tittori star, is strongly magnetized. So you have the star disk interaction certainly plays a role in driving the jet. And you have here three main classes of models that have been proposed, depending on whether the open magnetic field lines are anchored on the stellar surface, in the inner disk wind, or at the star disk interaction. And there are lots of recent numerical developments. why do we care at all to understand these jet launching mechanisms? Is because potentially jets and outflows could help solve two main important questions that remain open in star formation. Is why do Titori stars rotate at only 1/10 of their breakup velocity? And what is the process that allows matter to be accreted through the accretion disk? You know that I'm not going to enter into this, but we still do not know exactly by which process matter loses angular momentum in different regions of the accretion disk. And of course, if the disk is threaded by a large-scale magnetic field over a large radial extent, this will have important impact on the disk structure itself, so on the planetary formation and evolution. In particular, for example, migration properties. So I just wanted to remind a few, especially for the young people here in the audience, a few basic facts. So we now know that we have been knowing for a very long time with pioneering work of Sylvie Cabri, Susan Edwards, and many other people. We've been knowing that the presence of jet is linked to the presence of an inner disk and an inner optically thick disk even. And I show here recent results obtained by Pauline, because now we have access to a large amount of spectroscopic surveys that allow us to look into much more details into the properties of these jet signatures with respect to disk and stellar properties. And you see here, so that the presence of a high velocity component is highly correlated with the presence of a near infrared excess. And we've been knowing also that there's a high correlation between the ejection rate of the jet and the accretion rate onto the star. That covers really many orders of magnitude, and from brown dwarfs to Herbig stars, FEORs, and class 1 objects. And there are posters on this topic that you can look at. However, one point that I would like to make, one remark that I would like to make here is that probably the stellar magnetic field is probably not critical for the jet launching process. And why do I say that? Is because we also identify jets in a very wide variety of environments. So you can see here an example of a collimated jet emerging from an FEOR object. And we've heard that we know that FEOR objects are probably accreting at a very high rate, so that would quench potentially any magnetic stellar magnetic field that would be present. We have had evidence for the presence of an inner disk wind in FEOR stars from the early work by Nuria and Lee. And we also have examples of collimated jets from very massive young stellar objects, now up to 15 solar masses. And again, in that kind of environment, we may not expect the stellar magnetic field to play an important role. Another example I quote here is the jet from the Herbig A star, which has properties which are actually very similar to Titori jets. However, contrary to the Titori jets, where we routinely detect kilogauss magnetic field on their surface, such a strong magnetic field has been searched but not detected on this star. Nonetheless, I think the star-disk interaction is still likely to impact the ejection process of jet, even if it's not critical for jet launching, because we've been knowing also for a very long time that part of the ejection must originate from very close to the star-disk interaction, since we see these blue shifted absorption components in the permitted emission lines. And there's a recent result I would like to point out here. It's been obtained by Jérôme Bouvier first on the A8 system, then more recently Sylvia Alencar on the KH15D. So it's obtained on deeper systems where they evidence a correlation between the blue shifted and the red shifted, the velocities of the blue and red absorption components in the hydrogen lines, and that they interpret as a signature of magnetospheric ejections and periodic, quasi-periodic cycles due to the periodic inflation and reconnection of the magnetosphere, which I think is something really this kind of observations to pursue to constrain the origin of these components. Okay, so I go back to now to the result. Jet signatures. So it has been a long search for one way to distinguish between these different origins for the jets was to look for the angular momentum carried by these flows. So indeed, under the steady and axisymmetric assumptions, you can show that the specific angular momentum carried by the flow is proportional actually to the specific angular momentum at the anchoring radius of the streamline. And you can relate this specific angular momentum to the poloidal velocity of the streamline, and the relations are outlined here. In that diagram, so the disk winds occupy a very distinct location from the X and stellar winds. The X and stellar winds, since they originate from much closer into the star, of course, will carry much less angular momentum. So this has been a very tricky process, and people like Francesca Bacchiotti and Deirdre Coffey have been very instrumental in this topic. So we have few, to my taste, but that's matter of discussing. We have few very convincing evidence of global rotation of jets, and these are for me the two presented here. So it does not show up very well, but you can see on the left, so the jet from a class 2 source Digitao. On the right, the class 2, the HH212 ALMA observations by Lee, which show a systematic gradient across the jet perpendicular to the jet axis. And if you interpret that in terms of a steady axisymmetric ejection, you infer anchoring radii for the streamlines located between 0.05 and 3 AU typically. So really emerging from the very inner regions of the disk. You also infer, so what we call the magnetic lever arm, a moderate value for the magnetic lever arm. So I recall that this magnetic lever arm is the amplification, is the amount of angular momentum that such flow is able to extract. I would like to note that this conclusion, in these kind of calculations, we usually neglect thermal effects, which in the driving process, we assume that the whole driving process is due to magnetocentrifugal forces. And in fact, if you take into account thermal effects, you can show that these values correspond more like an upper limit on the magnetic lever arm. Another observational indicator has been tried to reveal the transverse structure of jets, because if jets are coming from, are originating from streamline anchored as different radii in the disk, we would expect an onion-like velocity structure with high velocity, high density material on the axis surrounded by lower velocity, lower density material. So these kind of observations are very hard to get, because you have here an example for the Digitao microjet, where we superpose at the same angular resolution the morphology, the intensity map for different tracers tracing different velocity of the flow. From the colors trace the high velocity iron 2 material, going from the high velocity iron 2 material to the low velocity H2 in yellow contours. And you see clearly the nested structure of the outflow. Which is exactly what we would expect in the case of a disk wind originating from a range of anchoring radii. I must say that not all jets show that kind of structure, and I show you on the right another example, the RW origami microjet, which reversely shows a very narrow velocity structure, which seems to point to, which seems more compatible with an origin for a narrow range of anchoring radii. Another question that we asked ourselves is how far in radius does a magnetic ejection could proceed? So there have been in recent years the report of possible candidate outer disk winds that we detect in the millimetric domain with ALMA through CO or SIO observations. And you have here a few examples through all classes, going from class 0 to class 1, essentially. So these are small scale molecular outflows. You see here on the order of 100 AU to 1000 AU typically, small scale molecular outflow that show consistent rotation. One traditional way to interpret these outflows is through interaction between a jet and an infalling envelope. So there have been numerous numerical works on this topic. I'm not going to go through all them. There are very few works actually look at the transfer of angular momentum between the jet and the envelope. And this one, where actually Lee was involved, did. So this is the hydrodynamical simulation of a wide angle wind interacting with a flattened infalling envelope. And they show that indeed the specific angular momentum of the envelope can be preserved, and they show that in that case they could reproduce some of these observations. In this case, the specific angular momentum measured in the case of the Orion source I small scale molecular outflows. However, I will show you in the following that we do have examples where we think that it's difficult to apply this kind of model because we have no trace of the envelope. And the first example that you've probably seen is the HH30 system. So HH30 is a class 2, Edge-on class 2 in Taurus that drives a jet that has been well known for a long time. But it also drives a small scale molecular outflow that you see here in 12 CO. Here is a disk that's mapped in 13 CO. The properties of this outflow are remarkable in terms that we can show if we look at the transverse position velocity diagrams, and you have one here. So this is a position diagram with here you have the transverse distance to the jet axis, here the line of sight velocity. And all along the flow, these transverse position velocity diagrams show ellipses. These ellipses can be interpreted as a emission from a shell, a narrow shell, a ring, essentially of gas. So, and by mapping the fact that the ellipse is tilted here is revealing the rotation of the shell. So by mapping these ellipses along the flow, we are able to reconstruct the 3D morphology and kinematics of this outflow. And we showed that indeed the HH30 is consistent with a hollow conical rotating outflow with a velocity rather constant expansion velocity of 10 kilometers per second, constant specific angular momentum. Another striking property of this outflow is that the mass loss rate in CO is huge. It's about 50 times the mass loss rate of the known atomic jet. We don't know the accretion rate onto the star in this source because it's edge on, so it's not very well determined. So the properties of this outflow are indeed fully compatible with what we'd expect from an MHD disk wind launched from a few AU in the disk with a very small magnetic lever arm, but still greater than 1. And these values are indeed very comparable to the recent magnetothermal wind solutions computed for magnetized disks by, for example, by Bai and Wang, and also the new low disk magnetization solutions by the team at IPAG. We have now another example of such outflow, and it's the outflow in DG-tau B. So DG-tau B now is a class 1 source in Taurus, which drives a very striking conical outflow that you can see here. That's detected out to a few thousand AU from the driving source. The specificity with respect to HH30 is this outflow is close to the plane of the sky, but not quite, slightly inclined. So this allows us to really constrain the transverse structure of the outflow. And you see here transverse position velocity diagrams for this outflow. So they all look the same along the axis of the jet, and they clearly show that the bright conical part shows a velocity stratified structure with high velocity material closer to the axis than the low velocity material. Again, so a stratified layer nature that you would expect in the case of a disk wind. Another important property of this outflow is that we detected around this bright conical cone of emission, we detect a low velocity still expanding outflow. So the bright conical cone is not tracing the interaction of the envelope with the envelope in this source. We could derive, so by we generalized the method we applied to HH30 to this source, and we actually could recover, we could map the VZ velocity and the specific angular momentum now in the outflow referential. So you see a clear velocity stratified structure of the outflow. The opinion goal here is not to scale. It's actually very narrow. It ranges between 20 and 30 here. And the map of specific angular momentum shows also an increase of the specific angular momentum at larger radii that would globally accept some irregularities. So again, this. So again, if we analyze if we average quantities along lines of constant VZ, we are able to derive constraints on the anchoring radii of these streamlines, which range typically between 1 and 10 AU. And again, we end up with the same constraint on the magnetic lever arm on the order of 1.6. Like HH30, we have here, we derive a very large mass flux in the CO component on the order of 10 to the -7. This is again more than 10 times the mass flux we know from the optical jet. So how can we interpret all these properties? If we plot here on this diagram again of specific angular momentum versus poloidal velocity, all the measurements from the DG-tau outflow, DG-tau B outflow with all the other known small-scale molecular outflows for which we have rotation measurements. And you can see that they do occupy more or less the same region in this diagram with the same range of parameters. So very low lambda values and anchoring radii typically between 1 and 10 AU. It's interesting because this is exactly the region in the disk where supposedly we have this problem of the dead zone, which means that the ionization level is not high enough to sustain MRI and to allow accretion. So that could be a signature of an MHD disk wind. What's interesting also is that MHD disk wind allowed to explain
5 minutes.
Okay, allowed to explain the very high ejection rate, the very high mass outflow rate we observe in these sources, because in this theory, the ratio of the mass ejection to mass accretion at the inner radius of the zone is a fraction of the is a fraction of the ratio of the anchoring radii to the power of psi, with psi measuring the ejection efficiency of the disk wind, and psi is in fact inversely proportional to lambda. So low lambda values solutions will have a higher ejection efficiency than high lambda value solutions. So this could explain why we observe such high outflow rates, and this may indicate a variation of the lambda values as a function of a radius, so getting maybe to higher lambda values in the jet launching regions. So this also means that these outflows may, the mass accretion rate reaching the inner radius of the disk are actually significantly lower than the mass accretion rate entering the outer regions of the disk. So there have been recent numerical as I was mentioning, recent numerical simulations of magnetized winds that indeed reproduce these results. But the big question now is to have a full thermochemistry predictions from these models, because it's not clear to us that the survival of CO molecules on such large scales would be possible. So I will go fast here. So this outflow, you probably don't see it, but we don't only have substructures in disk, but we now have substructures in outflow, and we identify substructures in the form of cusps at high velocity, arches at low velocity, which actually we can locate using under the assumption of asymmetry. We can locate these substructures in the tomographic reconstruction, and they have this typical shape. And assuming that these substructures in the flow correspond to originated from the disk, we can reconstruct the dynamical timescale as a function and anchoring radius. And we find typical variability, typical timescales between events of a few hundred years with a duration of the events on the order of 20 years. So it's a bursting CO outflow model, which with properties that are a bit intermediate between the EXOR and FEOR. Of course, there is an alternative explanation, is that these density bursts may also trace the interaction with a central jet through the form of bow shock. And I show here a recent hydrodynamical simulations not published yet by Benoit Tabon of a jet now propagating not in an infalling envelope, but in an expanding outer disk wind. That shows the formation of this typical conical cavity, although we don't clearly see the velocity stratification that we have in the observations. These multiple CO shells of substructures have been now detected in a few other molecular outflows. It's not clear if these are distinct shells or really substructure in an underlying outflow. And here I warn you, that interpreting directly channel maps is usually very difficult. You need, because of projection effects and kinematics, you need to be extremely careful. Okay, I will skip maybe quickly. So, so if all these jets outflows are of magnetic origin, can we detect the magnetic field? And for the moment, I would say that we do have, I will not talk about the disk because this could be a whole topic. Regarding the jets and flows, we do have some evidence that jets and flows are magnetic. But we don't know. At this moment, we cannot really assess whether the magnetic field is the main driving agent or not. Another open questions in my mind is that we always see this ubiquitous flow and velocity asymmetry, and in particular, so now we clearly see that jets can show a velocity asymmetry of a factor of 2 between the two lobes. And now we clearly see that this velocity asymmetry is established very close to the central source. So it's not due to the environment, but really to the driving process. And in that object, we could reconstruct the dynamical history of both lobes. And what's striking to me is that you see that both jets are ejected. The asymmetry in velocity is simultaneous over a time scale of a few years. And this, I think, is problematic, for example, for models of where jets originate from the star-disk interaction, where time scales are usually much shorter. Well, the HH30 CO flow is also monopolar. And we have now very deep observations that show that there is nothing in the south hemisphere where, although there is a jet there, that's so it's all these are striking questions and could be related to the magnetic configuration. I will skip to my summary. I'm open, lots of open questions actually. So I think now we have some evidence of MHD disk winds operating out to a few tens of AU. We still do not have a global observational picture. For me, the most pressing question is also the link between these resolved jets and outflow signatures and the spectroscopic signatures we see, like blue shifted absorption components, the narrow and the different kinematical components identified in the O1 line, which is the link between all these. I think GWST will be probably bring crucial information on this topic as it will provide a global view of the mass loss process on a few objects. On the numerical side, we do have sophisticated numerical simulations of the star-disk interaction on one side, and on the disk wind launching at large radii on the other side. But I think we now need to bring these two pictures together, because I do think that the star-disk interaction impacts what's going on at larger radii. Okay, and that's on this.
Thank you, Catherine, very much. So, questions. Lee.
This is really interesting. Could you go back to one of the DG tau? It was DG tau, right?
DG tau B. The one with structure, or the one?
Yeah, the one, you know, the way you had the two. It actually back further. Yeah. So so my first question is, both of those in the left-hand panel, that's all 12CO? Or
that's all 12CO. So the white contour is low velocity, 12CO, but it's like 1 kilometers per second from source velocity, and the bright cone is well, you see it in the transverse velocity.
Okay.
So The white cone is that part that's been integrated in velocity, and the white contour is that part, that lower velocity part here.
So do you think that inner 12CO is a cone, and that it's to explain the limb brightening?
Yes. Yes, no, there is indeed there is a limiting radius. Actually, when we go at high velocity here, it steepens, and there's a limiting radius. The emission doesn't go to the axis, so there's a.
So
it's hollow in the center, yeah.
So I have some other questions, but just as a comment, you know, you talk about the mass flux, and that's pretty interesting if you want to have anything accrete past it. But you know, it seems to me that like the important thing is perhaps the energy flux. So you have it in terms of like this lambda parameter or this psi parameter, right? But I mean, to 0th order, what you're looking at is the mass loss rate times the wind velocity as an energy flux.
Yes.
And then so then the question is, how does that relate? And we don't really know what the accretion rate is, I guess, in this.
We don't really know, yeah, but
so unless, you know, you're starting from farther out than the jet, so you have less potential well energy, and then you also have, and so then it's a critical thing about what's the ratio of the velocities of the jet versus this stuff. If this stuff is slow enough, then it's easier to have energetically that kind of mass loss rate. So
there's a factor of 10 between the two, because it's here we are at velocities of 10 kilometers per second, and there's a factor of 10, and
okay, so that helps.
No, one thing that I didn't mention, what's difficult to understand in terms of magnetic winds is the absence of recollimation, because if it's a magnetic disk wind on these scales, we would expect to see recollimation of the streamlines, unless indeed the jet inside pushes back on the disk wind streamlines.
Okay, we have actually a lot of questions on Zoom, but we've also run out of time. So I just would ask those people on Zoom to just put their questions on Slack, and Catherine can address those as well. So thank you again, Catherine, very much. Okay, so our next speaker is Emma Whelan from Maynooth University, and the title of her talk is Searching for MHD Disk Wind Components via Optical Forbidden Emission Lines, Spectral Astrometry. Okay.
Okay, so I just want to say thank you very much to the organisers from DIAS for giving me the opportunity to talk about this work today. And also thanks to Catherine for a really nice review of jets and winds. And basically what I'm going to be talking about today is about the low velocity component that we see in the forbidden emission lines of T-Tauri stars. And can we learn anything about it using the technique of spectroastrometry? So this was actually an idea of Ilaria Pasucci, and she got the time on ESO on the VLT to take the data. And I became involved really because of my long experience with this technique and because of the work that I have done on jets. And as Tom said, I'm in Maynooth University, so we have a small group there working on star formation. And I just thought, in case you're interested where Maynooth is, we're about 30 kilometers west of here. And also I should give a shout out to my students and just to advertise their posters, which I think are still available online. So we have Aisling, Matthew and Andrew presenting work, Muse data on 3 jets, and then Noah has a poster which gives a bit more information about the work that I'm going to be presenting here. Okay, so I have Lee's diagram as well, and despite what Catherine said, for this purpose of this talk, I'm really just interested in this part of the diagram. So in the picture I have in my head, like Catherine has discussed, is that we have a wind launched from the disk. We have the streamlines are decreasing in velocity as we move away from the stars, the radius increases and the inner part of that wind gets collimated into the jet, and then we have this outer wind, and we see this if we look at the velocity profiles of the forbidden emission lines. So we know early on in our studies of T-Tauri stars, we saw that they contained many forbidden emission lines. And one of the best studied one is the oxygen 1 line. And we saw that they had multiple velocity components. So we had this high and low velocity component divided on the basis obviously of the velocity. So greater than 100 kilometers per second, and we call it a high velocity component, and then less than 30 kilometers per second, the low velocity component. So this is a really nice spectrum of DG tau where you can clearly see this. The high velocity component is associated with the jet. And then the low velocity component is more compact. So there was an open question about what the low velocity component is tracing. And very early on, people like Susan Edwards, who worked on this, suggested it was likely tracing a wind. And we've had increased interest in this in recent years. So we've seen this paper by Andrea Banzatti a lot during this meeting, where we could further decompose this low velocity component into what we call broad and narrow components based on the full width half maxima. So if it's greater than 40 kilometers per second, we call it a broad component, and less than we call it a narrow component. So Andrea and others have done a lot of work looking at the velocities of these components, densities, the full width half maxima, and concluded that the broad component is likely tracing an MHD disk wind, but it's still an open question about the narrow component, and does it trace perhaps the photoevaporative wind, as Ilaria has shown maybe for some sources with the forbidden neon line. And why do we care? We care because we want to get a tracer of the MHD disk wind, because we have this competition between these two methods for which the angular momentum is removed from the disk, and Catherine touched on this as well. So is it an MRI or is it an MHD wind? And these recent simulations by they suggest that it's an MHD wind, and if it's an MHD wind, then in this wind the mass accretion rate should be comparable to the mass loss. So the mass loss rate in the wind should be comparable to the mass accretion rate. So if we can find a tracer of this wind, can we test this theory then? And just to note then that there's been many papers on this by lots of people that are here, like Pauline and Antonella, and the group of Brunella as well, who is online, and then the group of Ilaria has done a lot of work on this area as well. Okay, so basically we're going to see if we can learn anything new from spectral astrometry. And just a quick introduction to spectral astrometry. So basically what we have here is that we can take a typical seeing limited spectrum. So actually for the case of spectral astrometry, the atmosphere is your friend. And so if you it's easier to do with a seeing limited spectrum. So we take a simple spectrum and you're measuring the position of emission lines relative to the continuum using typically Gaussian fitting. And this means that you can recover spatial information from the spectrum below the seeing of the observation. So you can do better than the angular resolution. And this is illustrated here. And this is just an example from my first adventure, you could call it, with spectrostrometry. And so when I was putting these slides together, I realized that I got this piece of data 20 years ago today, or this week, sorry, and I've been showing it for 20 years. And I think it says much more about the technique and the usefulness of this, of the technique. But the first thing I did with it at the start of my PhD, we were looking at the permitted emission lines in T-Tauri stars. So we've learned about how they can trace the accretion. And this was the first time that I was introduced to the work of Lee. And these two papers were very important to this work. And we were looking to see if we could use spectrostrometry to disentangle the outflow component to these lines. And this is what we're showing here for DG tau. And this is the Paschen beta emission line region of DG tau. And using the technique, we were able to show that the bulk of the emission, so the red dots, was coming from the continuum position, so coincident with the black points here, but the wing emission was in the outflow. So this was important to understand. And of course, since then we have lots of imaging, the kind of work that Catherine does and Deirdre, and we've seen outflows directly in lines now like bracket gamma and Paschen beta, because we have the resolution to do this. And the beauty of spectrostrometry is that you can get really high accuracy if you can collect enough photons. So the accuracy we can get is just dependent on the signal to noise ratio of your spectrum. And it doesn't necessarily matter if you have particularly bad seeing. So if you're seeing as 1 or maybe 1 or 1.5, you know, that's okay as long as you detect enough photons. And it's been used in many, many interesting ways. So firstly, Bailey used it to look at close spectroscopic binaries. Myself and Tom did the early work on brown dwarf outflows using spectrostrometry to look at disk rotation, black holes, and recently people are looking at whether it can be used to detect planets forming in disks. So we learned in the last few days about these observations of planets. We see the H-alpha emission, so the planets are accreting within the accretion disks. And there's been some papers about can we actually detect this signature from the planets using spectrostrometry. Okay, so just back briefly then to this question of the outflow to accretion rate in the wind in the low velocity component. So Fang in his 2018 paper tried to do this, but the missing piece of the puzzle was that they didn't know what the wind height was. So they're estimating here L wind. And so this shows the ratios here or the efficiency here for a range of wind heights and for different gas temperatures also. And basically what this shows is that his results showed that the broad component is much less extended. It's more compact than the narrow component. And so it's unlikely that we could see this in the narrow component, that it's likely that in the narrow component, the efficiency is more like 1 to 10% like we see in jets, whereas it's possible in the broad component to have the mass outflow rate equivalent to the mass accretion rate. And so we wanted to see if we could learn more about the wind heights using spectrostrometry. So these were the targets that we looked at. So some of them were just single component targets. So they just had a low velocity narrow component or a low velocity broad component. And then some had a broad component or a low velocity component and a high velocity component. And I just use here the color scheme that's been used in other papers up until now. So the high velocity component is shown in green, the broad component in red, and the narrow component in blue. So I just have time to talk to you about one or two of these objects, but particularly was Oriolupi that we found the really interesting results for. And I think Oriolupi was the first spectrum that Nuria showed in her talk. So it's been studied for many decades now. It's a really interesting star. But just to talk to you first about we had to use a very specific strategy for these observations. So what we want to do was to take spectra aligned with the known position angle of the disk, but we wanted perpendicular and anti-parallel spectra. So we take 4 spectra, so 2 sets of anti-parallel spectra basically that are perpendicular. So we take one aligned with the disk, one anti-parallel to that, one perpendicular to the disk, and one anti-parallel to that. And the reason we do this is that we use the anti-parallel slit positions to remove artifacts in the spectrostrometry, and then we use the perpendicular results in order to do 2D spectrostrometry, so to recover the position angle on the sky of the signals that we're seeing. Okay, so this is what we saw for Oriolupi. So I have the oxygen 1 line on top and the sulfur 2 forbidden line on the bottom. And we see similar profile in both, in that we see a narrow component previously had been identified as a broad component, but we identify it here as a second high velocity component. But that's a detail that's not important for this talk. And then your high velocity component tracing the jet. And on the left and right then, the difference between these two is that the data are perpendicular. And the black points are the spectral astrometric results with the continuum removed. So the really interesting thing then is when we combine these to do the 2D spectrostrometry. So what we see here is that the red arrow is the position angle of the Oriolupi disk. And so you can see on the left for the high velocity jet, it's basically perpendicular to the disk as we would expect. The circles here show the 3 sigma accuracy in the measurements. For what had been previously identified as the broad component, we don't measure any signal here. And then for the narrow component, we see a signature. So this is the first time we have spatial information really about the narrow component. And you can see here that it's offset along a similar position angle as the jet. So this, it's perpendicular to the disk as well. So this was a very interesting result. But the most interesting result here is actually if you look at the velocity profile. So for the high velocity component, and this has been known in jets for a long time, we see material accelerating. So you see an initial increase in velocity with distance from the star. But we're clearly seeing the opposite gradient in the low velocity narrow component. So actually the lowest velocity material is the material that's offset furthest from the star. So this was the really striking difference between the jet and whatever is being traced by the narrow component. And this was a new result. And so if you make a plot, so here the distances are deprojected. So we have a plot of delta Z against velocity, and you can clearly see that the narrow component has the opposite velocity gradient to the high velocity component. And we were able to rule out photoevaporation here as the origin of the O1 narrow component because it's basically the wind is launched deep within the gravitational potential well of the star, and also the velocities we measure here are too high for photoevaporative wind. This signal has been seen for Oryolupi before. Oh, yeah, so I put this here to remind me to mention collimation. So when you're looking at this plot, it's easy. You might think, oh, the narrow component looks more collimated than the jet, but actually we don't get any information here about how collimated the emission is. So from the work of Andrea, they estimated that the opening angle or the semi-opening angle of the low velocity component is about 35 degrees, and we see much less for the jet. But with spectroastrometry, the spread here perpendicular to the axis is just related to the accuracy, which is not actually telling us anything about the collimation of the flows. This signature has been seen in Oryolupi before in the CO line. So this is what's here on the left. It's just comparing the Spectra Astrometry results reported in the Pontifidian paper and Klaus's paper in 2011 with what we see here. And we see the same. So they didn't have the perpendicular slits, so we can't recover the 2D information, but the morphology of the signal we see is the same. And how we're interpreting here is basically that we're seeing the velocity stratification that Katrine was talking about. So in the jet, we see the mixed material accelerating from the disk, and in the narrow component, what we're tracing is the decrease in the velocity of the streamlines as we move away from the star along the disk, but at the same time, we're seeing an increase in the height. And how we interpret this is due to the density profile in the wind. So this is the first time then that we can say that the O1, this forbidden emission line narrow component, is tracing a wind. I quickly just show you these. So when I was thinking about doing a new ESO proposal, I thought maybe we could observe the Oryolupi source to see if we could see the jet, but I discovered some narrow field, so 2 minutes, okay, some narrow field observations in the archive. And so this is actually the first image of the Oryolupi jet. As far as I know, it's never been imaged before. And basically this is what the image of the narrow component looks like to the broad component or to the jet. And I did a quick estimate of the width to try to estimate the opening angles. And you can see that the narrow component has a much wider opening angle, as is the work in progress, than the jet, in agreement with what Andrea estimated in his paper. And perhaps then, we see initially it looks much broader in the jet. So I think we're probably seeing the collimation region here of the jet as well. But this is work that my student Matthew is working on. So it's just a work in progress. So I don't have much time left. I just wanted to mention then for the single sources where we only see a broad component, we did the spectroastrometry, but we didn't measure any signals. And so this tells us that the broad component is indeed more compact than the narrow component, and is coming for, is far less extended. Okay, so what we did then was we used the method of FANG 2018 to estimate the mass outflow rate in the wind, to estimate m dot wind. And for the sources that only had a broad component, we used the 3 sigma uncertainty on our results to estimate the wind height. And clearly in Oryolupi, as expected, the efficiency is very low. So it's only about, depending on the temperature that you take, 5,000 or 10,000 Kelvin, it's about 1%. But in the broad component, the outflow rate we measure is much higher than the accretion rate. And if we estimate a temperature of 10,000 Kelvin, then it's about 30 to 90%. So it's still possible. If we refine our results further, we have to determine the correct temperature, that the broad component, that the mass outflow rate could be comparable to the accretion rate as predicted by the simulations. Okay, so I'll just go through my conclusions then. So for Lupi, this spectral astrometry shows that the narrow component is tracing an MHD wind, and it's clearly a very different signal from the high velocity component. We find that the broad component originates closer to the star than the narrow component as predicted by Andrea and by the Fang 2018 paper. And I was going to talk about TW Hydra, but I didn't have time. We see in the Muse observation that there is a clear difference in the collimation for the narrow component and the high velocity component for Lupi. This idea that the outflow rate in the wind is comparable to the accretion rate is still possible for the broad component sources. So of course we wanted to extend this work to a much larger sample of objects to see if Lupi is a unique case. So we got some more time to observe this winter, to observe this list of sources. So I'm particularly interested in CW tau and DG tau to see if we get a similar result for the narrow component. And this is just some high-res data. So actually high-res on Keck performs very similarly to UVIS and is just as useful for spectrostrometry. And so we did a quick test when preparing for the proposal on some archive high-res data. And you can see that we see a very we just have one spectrum, but we see a very different signature again in the narrow component than we see for the rest of for the high velocity component and the broad component here. So I think that we're going to get some further very interesting results from this data set. So I'll leave it there. Thank you. Thanks, Tom.
Thank you, Emma. Okay. Questions? No. Okay. So, well, in that case, can I ask you one about the so the general feeling now? I mean, I know a number of years ago we were thinking about the mass loss rate and the low velocity component might be very significant and something that we were ignoring. So your results are pushing perhaps in the opposite direction some of the time, or
no? So I think that was this was the whole motivation for the work, was to try to find a tracer for the low velocity for the MHD wind, and to measure the mass outflow rate. So I mean, it's just in this one case for the narrow component is clearly doesn't have a significant mass loss rate, but for the broad component, yeah, I think it still could be possible. So it's really trying to understand the origin of both, and yeah, I don't know if we're going to be able to resolve it with spectrostrometry, but the hope, we have refined the proposal here, or the strategy here to try to do that with the broad component in these sources. So,
okay.
Yeah.
So, right. Questioner at the back.
Thank you very much for this very interesting talk. I just have a very quick question regarding the low velocity component. When I understood it correctly, you said that we see that it has a slower velocity closer to the star and is then faster when it's farther away. And I would just, I guess it's like accelerated by a magnetic field, but do you know what has generated this magnetic field, whether it comes from the star or from the disk? Do you have any hypotheses about it?
What's this, the interaction region like Catherine talked about, the star disk interaction, but you mean for the jet is accelerating? Is that what your question? So you said the low velocity component. Yeah, so it's like what Catherine presented. My understanding is that you have a disk wind, and it's the inner part of the wind that is collimated by the magnetic field to form the jet, and then you have what remains then is the low velocity component.
Thank you very much.
Okay, thanks very much.
Okay.
Thank you, Emma. Okay, our next speaker is Simon Purser, and he's talking about a low power survey of the Taurus and Perseus molecular clouds.
Yeah, so good afternoon, ladies and gentlemen. Again, thank you to the SOC for giving me an opportunity to talk about my recent work. My name's Simon Purser. I'm actually a postdoc with Tom Ray over here. So I've got a friend as a chair, so hopefully not too many horrible questions. Yeah, so I'm going to be talking about my LOFAR survey towards 2 molecular clouds. In fact, just one, because that's where our preliminary results have kind of come from. So introduction material. Well, I think Catherine pretty much covered it all. So I'll ignore a couple of the points there and just highlight the accretion ejection link, right? However, one kind of little thing about jets, which is maybe either underappreciated or just not mentioned yet, is that these jets obviously feed back into the environment. Typically, you'd have this through the driving of turbulence in the molecular clouds. So they obviously affect the balance of the collective cores by driving support. But another mechanism supporting these clouds is the enhancement of magnetic support due to the production of low energy cosmic rays. Low energy cosmic rays, of course, ionize the environment and hence provide that added support. So jets do play a role in star formation in many ways, and this is the way I'll be concentrating on today. So how does the driving of this cosmic ray production at shocks in the jet, how does that influence the star formation paradigm? This is like, I mean, we've already talked about DG tau. I think it's probably, is it the most covered object in this conference? I don't know. So I'm going to cover it again. This is actually an RGB image. The background is an RGB image of I band in red, H alpha and S2 in green and blue. And you see shock emission in the green. This is obviously an optical image. And then you see radio emission, essentially at the bow shocks, which is in the contours. And this shows non-thermal populations of electrons, hence cosmic rays, right? I'll just skip that. So when it comes to the actual radio emission from these things, from the jets themselves, there's a few emission mechanisms, and up to about a year ago, before Anton, who's here, did his work on variable T-Tauri stars in the radio, I was only aware of the top 2 emission mechanisms. You have your typical kind of thermal emission from the jet itself, which is Bremsstrahlung, and that has a very predictable spectral index in the radio and 0 polarization typically. You have synchrotron, which is emission at these shocks via the production of non-thermal electrons. And then you have the other 2 types, which come from coronal loops or exaflares or star-planet interactions. And this is the electron cyclotron maser mechanism and also plasma emission. So the telltale sign for these 2 types of emission in the radio is that they're extremely variable in the short term. And that's what I kind of want to look at today. So previous work in the field, there hasn't been a great deal of low frequency radio emission. I feel like radio astronomy is kind of the ugly brother of optical and infrared astronomy and star formation. We don't get talked about much, but we're trying. And the low frequency survey by the GMRT, which is an Indian radio interferometry by Ranger Lanesworth in 2016, essentially surveyed 3 fields with known emission from T-Tauri stars. And these are actually 3-pointing. So you'll see these as circles. This is essentially the sensitivity fields of the primary beams of the radio telescopes. Unfortunately, aside from the 3 radio emitting, or sorry, the low frequency radio emission towards 3 T-Tauri objects, or sorry, 3 YSOs in the field, which are DG2A, L1551 RS5, and T-Tau, they actually didn't detect any further YSOs. So what you can do is you just drive down the frequency to try and pick up non-thermal emission because it's brighter at lower frequencies, right? Importantly, one thing I forgot to mention is they actually produced a catalog of 2,000 extragalactic objects. And this shows how complicated it is trying to tease out the galactic emission when there's so much extragalactic stuff out there. So I guess I don't really need to recap this slide, but the motivation for this particular survey was derived from Tom's, well, it is part of Tom's EASY project, and it's trying to determine this low energy cosmic ray contribution from jets. You can also do other things if you sample a radio SED along enough frequencies, such as constrain the jet launch and collimation mechanisms, which Catherine alluded to before. And then you want to kind of get a measure of how common these exaflares and coronal loops are in YSOs, because that is just a developing field. And obviously I've just highlighted kind of the radio emission mechanisms responsible for all these different motivational aspects. So got to pick a YSO sample. And I'll just talk about Perseus. Now, there's a lot of catalogs out there. For a radio astronomer looking through an abundance of infrared catalogs, it's a confusing world. So I just stuck to the good old trusty C2D samples of Evans and Dunn et al., hoping that these were our bona fide sample of YSOs towards Taurus, and that's about 385 different YSOs. So this is as if you've not seen it before, right? This is the Perseus Mercury cloud seen in 2 mass-derived extinction mapping with sites of star formation labeled, and then individual YSOs as the colored markers. So as for our observations with LOFAR, I know that you probably won't be too familiar with the LOFAR telescope, so I'll briefly introduce it. The LOFAR telescope, this is actually called the Super TERP. It's one of my favorite acronyms, that's a good word, acronyms in physics. And essentially it is the central cluster of radio stations in the interferometer array. And you have 2 different types. You have the HBA nodes, which I've highlighted in red, and you have the LBA or low band antenna nodes, which are highlighted in blue. And these have different bandwidths of operation. And I'll just be focusing on HBA stations. Now, the LOFAR telescope itself has stations all around Europe. In fact, there's one just down the road in Bur, which is probably about an hour-and-a-half drive away, which DIAS has an interest in. But unfortunately, I won't be using all of the international baselines because calibration for those is a bit of a nightmare. So I'll stick to basically the vicinity of the Netherlands, which is the remote stations. Now, luckily, Taurus and Perseus are fairly close together, so we can survey them in pairs of pointings. Pointing is the radio astronomy term for you stare at a point in the sky for an extended period and integrate the visibility into one image. So Perseus is obviously up in the top right, and that was covered by 5 pointings between the frequencies of 120 and 168 megahertz. This was done with the Lotus survey, which is surveying the entire northern hemispheric sky. And essentially each pointing was 8 hours, and that drove down our sensitivities in these regions to about 85 microjanskis per beam, which, to be honest, at these frequencies, which is about a central frequency of about 140 megahertz, is pretty good. And yes, I've got to mention it's a 6 arcsecond resolution. So in terms of the imaging, we take the data sets. The data sets themselves are quite extensive. You're talking multiple upon multiple terabytes. So it takes about a week to reduce each field. Luckily, I don't do it. I just give the hard work to the guys in the Lotus survey. They share the images with me, and then I further reduce their average data sets into single-hour images to check for variability. There's 24 of those. And then to try and get a measure of the radio spectral index, I image them in each of the individual bands. To get a measure of the polarization, I then image, or I don't image, I get given the Stokes-B images. So now I've got a measure of the variability, the spectral index, and the polarization, which are all these things that I need to try and tease out the emission mechanisms towards each object. So as for the results, this is, I guess, the PMC. The contours are the extinction map by Debashi et al. In 2005. I think it's CO extinction. I think the extinction magnitudes there are 1.5, the outermost contours. And you see the radio map in the background. So the first thing that strikes you is the number of sources in this image. And as you start driving the sensitivities down, essentially your extragalactic population, your image explodes, and you start having a problem with source confusions. So as a result of the source confusions, you need a decent way to tease out all the individual sources. Luckily, there's a pretty decent package called PyBDSF. I don't know if anyone's familiar with it. It stands for the Python Blob Detection Source Finder. And essentially in radio astronomy, because you're only partially sampling what we call the UV plane, you have a lot of image defects around, especially around bright sources where you're what's called dynamic range limited. So you play about the settings a little bit and you make sure that how pi BDSF works is it picks out sources based on the local RMS and not the global RMS. Anyway, you do that and you associate in each of the images, all of the epochs, all of the bands, each source within 3 arc seconds of another source is defined as the same source, and you end up with a total of about 40,000 individual sources, which we've now got to attribute to YSOs. I'll skip over this slide very briefly, but just to say that when we actually calculate spectral indices of these things, the average spectral indices of the sources are about -0.5. Takeaway message of that is it's just dominated by extragalactic sources. So we need to be sure about what we attribute to YSO emission. In terms of kind of the moving on to kind of the analytical part of the work so far, anyway, this is a work in progress. We have to define the radio emission in 2 kind of ways. So taking the prototypical non-thermal low mass YSO source DG tau A, this is the anatomy of DG tau A, boiled down into a schematic. So you've got the central disk with the red jet going away from you towards the northeast, blue jet coming towards you in the southwest. The blue lobes you see are the non-thermal emitters, and anything red is a thermal emission from the jet itself. So we know that the non-thermal emission is always separated from the central object. So we define 2 categories of emission. Anything that is within 3 arc seconds, i.e. beam width, radio beam width, the actual AR YSO is defined as YSO. Radio emission, and anything within 15 arc seconds, which is an arbitrary value, defined as YSO associated. Using synthetic extragalactic catalogs, we define the chance of a coincidental match with a spurious extragalactic source. These are the kind of rates we get. So about 4.5 per catalog of 100 YSOs, we should expect 4.5 of those to have a spurious extragalactic detection. This is a typical kind of imaging result. So as Antonella Natta says, potato studies, they are just blobs, but you have the 2 types of emission around this particular C2D YSO. So I'll skip over that. This is just the kind of the low far emission are potatoes overlaid on infrared images, I believe Spitzer RGB images. And you see obviously the associated emission centralized on the actual YSO itself. In terms of variability, this is a plot of variability by the hour, so flux against time epoch. And you see that these sources, potentially without the bottom left one, are actually fairly constant in the variability, which produces a problem with the emission mechanisms. So this is just a little movie just to illustrate kind of the, well, it's not very intuitive, but what it's supposed to say is that these things are fairly constant apart from the bottom left YSO. This is actually a plot of what the quantification of the variability, which I call the coefficient of variation, against the 144 megahertz flux. So you see kind of these dynamic range limiting side lobes, the image defects on the right, you subtract them from the total sample and you see a lot of structure. The green dots are where essentially our YSOs, our YSO radio emission lies. So you see it's A, non-variable, and B, quite weak. Just the only point to make here really is that they're all from quite a limited range in bolometric luminosities from the C2D sample. Quite low luminosity objects with a range in infrared SED classes from 3 actual flat spectrum sources to a relatively under-evolved 0/1 class and then a T-Tauri class 2 at the bottom. Importantly, none of these displayed any polarization. So I'll skip over those. Essentially, the takeaway message is anything that was within 15 arc seconds is most probably going to be extragalactic because we expect a lot of extragalactic contaminants at that spatial separation. Taking it as a lower limit. So we don't have any detection of non-thermal emission separate from the central YSO. If we assume an equipartition between the magnetic field, the energy in the magnetic field and that in the non-thermal particle populations, essentially we end up at a contribution to the galactic low energy cosmic ray energy density of about the same level as the currently existing galactic cosmic ray energy density. I am running out of time, but essentially when you then plot them on a radioluminosity versus infrared luminosity plane and compare them to previous results of known objects, you actually see that they occupy quite a narrow range in bolometric luminosity, which when you actually look at the emission properties themselves, you can actually deduce they're not thermal emission from jets, very likely not star-planet interactions like we see with Harry Vedantam's work. And they actually may be more similar to Anton's variable emission, which is his Anton Finio-Hansen's 2021 paper, which was just published. So just because I'm out of time, I'll just put my conclusions there and just highlight the fact that essentially we don't see any non-thermal emission, and we've constrained the contribution to this low energy cosmic ray flux from jets in the PMC. So I'll leave it there. Thank you.
Yeah, so we have a question, sorry.
Yeah, so we have a question from Marina, if you want to unmute yourself and ask.
Yeah, so since you have observations of both Taurus and Perseus, and Perseus itself has multiple clusters, do you observe any differences between the different populations?
I'm sorry, could you just repeat that? Sorry, Marina.
Do you observe any differences between different populations, such as between Taurus and Perseus, or in Perseus between different clusters?
Okay, sorry, yeah, I actually skipped out the Taurus results because the Taurus results are still preliminary, but I am hoping, yeah, they will be coming. But the Taurus population, I am hoping, will constrain this cosmic ray, low energy cosmic ray flux a little better, because obviously it's half the distance. So yeah, stay tuned.
Lee, yeah.
Said that very deliberately, Tom. So this is a completely stupid question, but there are, because I don't have any feeling for the wavelength range, but you know, there are some at VLA wavelengths, you know, 10 centimeters or something, there are non-thermal binary sources. Would those things be detectable at low FAR at lower frequencies if they're non-thermal emitters?
I've actually not done any analysis on that or thinking about that, but I'd certainly be keen to discuss that possibility, especially because the emission mechanisms themselves, in fairness, they're not very well constrained. All of those emission mechanisms that I listed, on the basis of the low polarizations, I am looking for alternate explanations to the low frequency radio emission, especially since I've ruled out extragalactic pollution. So, yeah.
Yeah, so just to answer that, I mean, there are one or two sources that were known a couple of years ago. They're high mass sources. There's a high mass source, HH8081, has non-thermal emission, and there is polarization there. But what Simon's looking at is the more lower mass objects and trying to understand how much they can contribute.
It's just that, for example, Marina and Laurent Lennard had done this thing in Orion where they got a bunch of these things, but low mass objects, but typically binaries. But maybe, you know, Orion's farther away, so maybe they're too faint or something.
Question?
Simon, I was just wondering, what energy do you get for the cosmic rays? Are you able to estimate what energy you can accelerate to in the jet?
Are we talking energy flux or?
Like the cosmic ray energy, so.
As in, you're talking giga electron volts?
Yeah.
It's gone out of my head, but this was something that I calculated.
Oh, it's grand. You can calculate
yeah.
ask later. Thanks.
Okay, thanks very much. I think there's some more questions on Zoom, but again, they can you can look at those on Slack. Thank you, Simon.
Thank you.
So our next talk is on 9, and it's Jaime Vargas Gonzalez, and it's on high energy processes in Orion YSOs with the VLA, ALMA, and the VLBA.
Perfect.
Great, thanks.
Thank you. So, well, let me first give a big thanks to all the organizers. It's been a very useful conference for me, and it was a good idea to make it in a hybrid mode. I appreciate it. And of course, congratulations and thanks at the same time to Lee Hartman. It is evident your contribution has made a huge progress in the field. And I've seen from testimony from people that also an impact in the professional life of many. So congrats and thanks for that. My name is Jaime Vargas Gonzalez, a PhD student at the University of Hertfordshire. I talk about ready variability in low mass protostars as a tracer of high energy processes, thus providing a complementary perspective to what X-ray studies have done in the field of protostars. I've been working with Jan Forby, Sergio Ziv, John Bali, and Victor Rivilla. We have seen in the last days that there is a range of multi-wavelength properties during the evolution of low mass stars, particularly in the T-Tauri phase due to the presence of circumstellar disks, outflows, jets. So we can detect radio emission from YSOs from a range of size scales. And depending on the scales, we can see radio emission in the form of thermal and non-thermal emission. From my perspective, what I say relatively large scales for me, we can see thermal radio emission from circumstellar disks, also from ionized material at the base of stellar jets, outflows. And then we have non-thermal radio emission at the smallest scales, where we also see thermal X-ray emission. So to describe this part, I struggled to choose an illustration. We have several options. Also this beautiful illustration from the gravity collaboration that Rebecca Garcia Lopez showed us on Tuesday, I guess. But of course, why not? This is this conference. I need to use this, of course. So at the smallest size scales, we find this complex magnetic field structure, which is also responsible for the thermal X-ray emission. Here, the electron populations urating along the magnetic field lines can produce non-thermal radio emission, both at centimeter wavelengths and millimeter wavelengths, gyrosynchrotron and synchrotron respectively, depending on the electron energies involved. So my goal is to study these processes at radio frequencies, but for a large sample of YSOs. So here I start with the at centimetric wavelength using the VLA towards our old friend, the Orion Nebula cluster, using this the very large array. So the particular thing with the ONC is that without doubt, it is the ideal place to detect hundreds of sources in a few arc minutes, using even just a single pointing with the VLA. So it started with a deep VLA catalog that Forby and collaborators reported in 2016 towards the ONC. Here I'm showing you a reference optical image from HST, where they use the C-band, 4 to 8 gigahertz, 30 hours on this field, and covering this area. For reference, I put here I hope you can see the trapezium cluster. So then after this survey, we extended with 4 years later with observations repeating the central pointing, but including 6 adjacent pointings, all of them 5 hours observations. We are now covering this large area, almost 20 per 20 arc minutes. So we enlarged this census of centimeter compact radio sources, expanding this large area. We found 5 and 20 compact radio sources. Almost 200 are new sources not previously reported at these frequencies. So the idea to cover this area is to match also the CUBE X-ray survey, which is the most complete X-ray survey in the ONC. And it's the best available tracer for the young population in Orion. So since we have this large area and we also have near in the center the trapezium cluster where the most massive sources are, we can first see how is the properties of the radio properties of the sources in the area. Here I showed this plot, peak flux density of the sources against angular distance or also linear distance in parsec. away from the most massive source in the trapezium, the θ1 receive. And we can see this decreasing trend. The colors here, the grays are all the sources we detect. In blue, the ones that has a X-ray counterpart, so most likely YSO. And we see this decreasing trend until at a distance of about 0.3 parsecs. So it is suggested that this ray emission is higher, closer to the most massive stars. So probably we are detecting this thermal free emission from these externally photoionized circumstellar disks. And as you go farther away, you don't see the thermal emission from external photoevaporation, but then you start to see probably the non-thermal emission intrinsic from the central object in this young stellar system. Now, in order to highlight the sensitivity of VLA observations, I want to show this additional finding, just comparing the two observations, the first VLA central pointing and the second VLA central pointing. They were observed with 4 years difference. And we found proper motions just comparing this exactly almost absolute astrometry maps, astrometric solution for these maps. And there are these very fast radio sources with velocities of up to 370 kilometers per second. This is hard to be a star, of course, it's too high, but actually this belongs to an explosive structure of the OMC1 also, this fast motion. You might remember from the Adam Ginsburg talk, where he mentioned this interaction of stars and how that can impact accretion. But this interaction of this massive star was what triggered this explosive structure, and where we find this fast proper motion. So this is a near infrared image of this explosive bipolar outflow, and this is the red vector shows the proper motions that we found from the VLA data, and this is how it looks in the centimetric VLA data. We don't see in the radio the entire structure, but we see how the emission comes in top of these bullet-like features. We don't exactly know where the radio emission comes from, but it seems to be from the densest part of this ejecta in this bullet point. So this sensitivity is crucial if we want to look for variability at very short timescales, because we can detect YSOs, for example, on timescales of hours or minutes. So this is why that sensitivity is important. I'm showing here light curves of a particular source in the first VLA observations reported by Forbit collaborators in 2017. These are 3 light curves for the same source at 3 different time resolutions. 7 hours in this case, and we see the concatenated, in this horizontal line, the concatenated flux from the entire data, the individual epochs peak flux density, and then you by doing time slicing imaging, you go into shorter time scales. The middle light curve shows images of 30 minutes only, and where you can see this in the third epoch, how a flare starts to show up at these short time scales that you couldn't see in the concatenated data. And it becomes more clear if you go to even shorter time scales, where this is a flare of almost an order of magnitude, if you go to time scales of minutes. So in the first VLA observations, there were about more than 10 strong flares. Strong flares are above, with changes in flux density above a factor of 10 in a few days, a few ones even in time scales of a few less than an hour. So taking this into account, now using the new VLA data we got, I imaged these maps into very short time scales of 5 minutes intervals. So the new central pointing in the new VLA data spans 5 hours. So this gave us 40 images on where we find this variability. I'm showing here some examples of variable sources in the new VLA book. Also, again, the average peak flux density in this gray band here. And then you can see how in this short time scale, you see this increase in peak flux density of the source. We do not find some strong flares in the new data, but we still find a change in variability factor by change in peak flux density by a factor of up to 5 in a few minutes to hours. So just taking into account the both VLA observations and the amount of extreme events that we find, we could say at the moment that these extreme events happens every 3-4 months. But there's quite a large scatter because we don't have too many events to put into our statistics. So if we now compare the long-term variability, just comparing directly the sources that were detected in both epochs of the VLA observations, there are some sources that in this range of 4 years, there is a difference in peak flux density by a factor of 10 in a few sources. And now, this is in the centimetric range, but we saw that there is also the possibility to find some non-thermal emission and at millimetric wavelengths. But usually in the millimetric range, we are using these frequencies to trace the thermal dust emission from circumstellar disks. And this is a constant dust emission. But it can happen that if there is a flare with electrons, high energy electrons, you can detect some non-thermal emission from cyclotron emission. But how often does it happen? We actually don't know how often because we don't have a strong statistic of it. And there is indeed just a few examples in the millimeter range. Here I show an example in the left side, reported by Bauer et al. In 2003. Also looking at the ONC with BMAT 86 gigahertz. And this young star object, this is a young star, suddenly became the brightest source in the entire nebula or in the entire field that they were observing in the ONC. There is another example, for example, reported by Masi et al. 2006. This is a binary system, but it also showed a flare in a time scale of a few hours. But in order to answer the initial question, how often does it happen in the millimeter range? We are using now ALMA millimeter, 3 millimeter continuum maps, covering, also looking at the Orion Nebula cluster in the inner part. As a reference, I'm showing here the trapezium cluster. So we are covering about 0.2 parsecs in area, 8 epochs of 1 hour each. We find in this very complex map around 120 sources. And just looking at the maps, these individual 8 epochs, there is several sources, but these 120 are the ones that I detected in the concatenated data. But when I went to look into the individual epochs, there is this flaring source that wasn't detected in any other epoch, but only here in the 4th epoch with a signal to noise of about 20. This is coinciding with the position of a centimeter flare source detected with the VLA reported by Forbrick in 2008. So this is a flaring source, an example where you cannot see anything in the concatenated data. But overall, the range of variability that we find in the millimeter range in the ALMA data is shown in this plot here. Just to remind, the VF that I show in this axis is basically the maximum change in flux density in the light curve of the ALMA light curve. This ALMA light curve, correct, is just from hours to days. And we find this range of variability of up to a factor of 6, and a lot going on at lower degrees. But since the Orion Nebula cluster is very complex, there is extended emission, sources close each other, it's not an ideal place to where you have a clear background and you detect the flux from the source. So in order to assess how much spurious variability we can find from this analysis, I performed some simulated observation to see, try to reproduce our actual ONC observations, but expanding a range of elevations. So I put artificial constant sources, and we find that only because of the changing shape of the synthesized beam size, the synthesized beam, we can reproduce a spurious variability of up to a factor of 2. But this only happens in the context of the ONC, where there is a complex map or a complex region. So if we have an ideal case on where there is no complex emission, or you can detect the entire flux only from the source, it can be done with the BLBA, where the spatial filtering is so extreme, you get rid of all the extended emission, and you're only detecting the flux from the central star itself. So that's what we get also observing, making a follow-up of the VLA detected sources. We are looking with VLVA, sorry. With VLVA, we don't have to image the data. We can get the extracted flux directly from the UV data. Then we get rid of this systematic variability that we can find from time slicing imaging. This is just an example of one of the sources that we detect in VLVA data. We got 4 epochs, and there are more epochs coming soon. This is a YSO system. There is some variability at short time scales, but there is also more variability at long time scales. In short time scale, we find variability in this sample in the range of up to a factor of 5 or 6, and in long time scales of a few years by a factor of up to 8. So with VLVA, since we can extract directly from the UV data, we can generate light curves at any time resolutions that we want without imaging. Is very efficient, and it will represent the largest sample of VLVA light curves of YSOs, looking just at the ONC. I will leave there the conclusions, and yep, happy to take any questions or in a Slack if there is no much time. Thank you.
Thank you, Jaime. Questions? Okay, so you.
There's one on Slack from Lynn Hillenbrand. If you want to unmute yourself on Zoom as well, that's fine, or I can read it out.
Oh, the comment was simply that regarding the X-ray selected samples, it's not the case that every interesting or every ONC member is actually detected in X-rays. So I wouldn't make that restriction in the analysis of the radio data. And you forgot the most important comment I made, which is it's very interesting work.
The very interesting, I missed that this last part.
Oh, I think your research is very interesting.
It's just, yeah, but that's true regarding to the X-ray. Even, yeah, not all there are some YSOs confirmed that they weren't detected in the X-ray survey. Is the most, is the best tracer for the young population. However, it's not the definite answer to disentangle without a YSO against any other kind of source.
There's a question on Zoom from Marina as well, if you want to unmute and ask.
Yeah, so I'm very curious about these non-stellar objects that you identify and you get proper motions for. Do you think there may be other non-stellar objects without proper motions, or the ones that would have a smaller proper motion that you might identify in the sample?
There might be some other also related to the same event, this explosive structure, because since this structure is there are sources moving in every direction. So in these 4 years, we were able to detect the most significant, the ones that are basically moving in the plane of the sky. But if we have, for example, a longer time baseline, we might be able to detect also non-stellar sources that are moving towards or far away from us, that in 4 years, they will be in the same part, but could be in a different position if with a longer baseline. So there is also some non-stellar detections in the VLA data, but related to some jets. For example, the VN source, there were some very faint features, also compact radio sources, but are alleged to be, we think that these are part of the VN jet.
Is there a reliable way to separate them other than proper motions?
Oh, sorry?
Is there a reliable way to separate them other than proper motions?
To separate them, or it would be ideal to have a spectral index, but usually these non-stellar sources are not quite bright, so the signal to noise is not enough to get spectral indexes. So I think the proper motion is a very usable for disentangle source identification, but since they are so faint, it's a bit more complicated with other methods.
Thanks.
Cheers.
Yeah, just to follow up on Marina's question, I'm just curious about the, so these non-stellar sources, as you're calling them, I would presume they're basically just the thermal Bremsstrahlung emission behind essentially non-visible HH objects near the core. Is that correct? And in which case, you should be able to get an estimate of what the implied mass loss roughly is as well, at least in the ionized component.
That would be ideal. Some of these, well, not these ones, but a few ones are detected in HST images. So at some degree, we could use those data combined as an approach, but I haven't done that analysis there.
Okay, thank you.
Yes, sorry.
Thanks. Our next talk is by Hector Arkay on outflows from young stars and their impact on the star formation process. So we'll give you a warning at 5 minutes, Hector. Okay, thank you.
Well, thank you very much for inviting me to give this talk. I am truly sorry for not being able to be there and in person, seeing you all, talking to you during the coffee breaks, etc. But the second best thing to do is to do it online. So I was asked to talk about the impact of outflows, and we've already seen talks that discuss outflows, but here you see a schematic of the different manifestations of outflows. Outflows can be seen at different wavelengths, and they are and the different kinds of emission are produced by different physical processes that take place in this important phenomenon, the star formation process. We heard about the optical and the radio, but I'll mostly be talking about in the millimeter. Basically, the entrained gas, the gas that has been pushed and accelerated by the wind from the protostar. And this is good because I'm talking about this one because it's the best, I think, it's the best probe for trying to see what the impact of the outflow is on the cloud, because this is, again, entrained gas. It doesn't cool as fast as the shocks, which cool in around 100 years or so, or a few hundred years. And so molecular outflows are a good probe of the mass loss history of the system. And so why this particular topic, the impact of outflows, is important? Well, let's go back to the first paper that was mentioned in this conference back on Monday. And I had to thank Lee for this, because in his paper with Javier and Ted, they talk about rapid star formation. But in order to have that rapid star formation, they also talk about rapid dispersal. As if you notice here, the clouds that they mention here, which are still forming stars in the table 1, most of them are low mass stars. And with no high mass stars that could form H2 regions or go supernova. So there was still this, or there still is, I think, this problem of how to disperse regions that only form low mass stars. And they talk about this in this section about dispersal and also in the conclusions. So one of the issues is, how you disperse this low mass star forming regions, which don't have supernova or H2 regions to provide the feedback. And one possible source of that feedback will be outflows. And so back then, around 2001, we started seeing, even before that, we started seeing giant HH flows, and we started seeing mapping those, how those giant HH flows would look in the millimeter, how they look in the CO, what kind of molecular outflows they entrained. And there were several giant HH flows that were mapped in CO, and we could compare their energy and momentum with that of the cloud. And it seemed like they could provide a lot of energy, and the momentum that they had could disperse a significant fraction of the small cloud where they were forming. And I highlight what I call the escape mass, which is basically the mass that you would be able to escape, that the mass that will be able to escape if you put all the momentum of the outflow into trying to disperse that mass from the cloud, given the escape velocity of the cloud. And if you could see the outflows these are giant outflows below this red line, those can have energies that are larger than the gravitational binding energy of the small clouds, and also they could disperse a lot of mass. But again, these are outflows that are forming that come from stars that form in very relatively small clouds. But okay, we'll say this is one small cloud. So how about if we extrapolate this and say, well, in molecular cloud complexes like Perseus and Taurus, where only low mass stars are forming, you could have many of these giant HH flows, and maybe those can provide the energy and momentum to disperse the cloud. And so we went ahead and tried to, and me and other people actually went ahead and tried to search for molecular outflows in molecular complexes. And this in particular is Perseus, where we did find, the known outflows, many known outflows that were unresolved, but we also detected outflow extensions and new outflows. And this you can do when you have a map of the entire molecular cloud complex, which were coming online in the early 2000s, mid 2000s. But what we found is that, as you can see here, outflows are of course concentrated where stars are forming in the different star forming regions in Perseus. And they do not, that you don't see that many giant HH flows or at least giant CO outflows that would provide the energy or momentum to disperse the cloud. But this was not the only survey. The Perseus cloud was not the only cloud that was surveyed. Adam Ginsberg, he surveyed the W5 cloud, and other people surveyed other molecular clouds. And it was clear from the surveys that the energy or momentum of the outflow was not enough to unbind the cloud. So it seems like outflows are not enough for that. But it was clear that outflows were concentrated close to where stars are forming in those regions. So instead, we'd focus to see what the impact of the outflows were on this star forming clumps or cluster forming clumps, and we did a survey. In that same survey of the Perseus cloud, we divided the cloud into different, let's say six star forming clumps. And so here they are. Most of you probably know them. And let's see, what we saw was that indeed the outflows did more, had more impact on the cluster forming clump. But still, again, you're looking at the escape mass. It was only around 5 to 20% at the most so of the gas that could be dispersed from the looking at the total outflow momentum. Maybe we could multiply this by a factor of 2 to 5 if we assume a constant total outflow momentum over the lifetime of the cloud. In order to, these are regions that were about 1 to 2 million years. So if we assume that the star forming regions only live for about 5 million years or so, then we could maybe do this calculation or add in this factor. or even assume that the star formation rate would increase more than what it had been. But you need all that in order to disperse quite a lot of the mass in these clumps. What we did find was that in fact the outflows had enough energy or input enough energy to drive the turbulence in these clumps, but that was not that is consistent with what then Nakamura and Lee found in 2014, where they mapped and they took the data from the literature, looking at how much momentum and energy the total outflows were injecting in the different star-forming clumps. And indeed, they find that the outflow momentum is significant and can drive the turbulence, similar to what we found in Perseus, in the different places in Perseus, but that it's not enough to disperse the cloud. And there have been other project or studies that find similar things that I list here. So outflows lack the energy or momentum to cause any major cloud disruption or even drive turbulence at the scales of molecular cloud complexes. They do impact, like I said, in the star forming clumps, but not the entire complex. So then, if you believe that feedback mechanisms are the ones that, or internal feedback mechanisms are the ones that are responsible for dispersing the cloud in molecular cloud complexes, then you need other feedback mechanisms. So we thought that maybe the spherical shells or bubbles or bubble-like things that we found in Perseus could do this. We did as with the same data that we did the outflow survey. We found different, like 8, I believe, I don't remember how many, whether 14, 8 shells that we found in Perseus, and here are some of them that are presumably driven by young stars in this star-forming regions that do not. This star Perseus does not form high mass stars, so there are no H2 regions in this cloud. These are shells that are driven by low to mid mass stars. So I think this might be a little crazy, but looking at the literature from years past, we see that Ali and Nuria have at least 2 papers on this, where they talk about the winds from T-Tauri stars, at least spherical symmetric models, and where they suggest that the mass loss rates have to be around 10 to the minus 8 solar masses per year, certainly less than 10 to the minus 7 solar masses per year. Just to be sure, this is not the first paper that Lee was involved in terms of T-Tauri winds. There are some with Susan Edwards and other people there earlier. So Lee has been interested in this particular field for a while. Also, this paper that is not very well cited, I think, but it's to me it's quite important. I think it only has like 33 citations compared to 400 something with the Hartman et al. 2001. They both came out around the same time, where there's this where Jack Welch and Lee Hartman and Tamara Helfer and Sergio Briceño, they mapped this. They discovered this what looked like a expanding shell around XZ tau, and so this it could be that the shells that we found in Perseus were similar to the ones found around this T-Tauri star. And for the benefit of the people in the audience, and especially before Carl and Maida asked me about this, here's XZ tau, and I believe this is the shell around it, where the edge of the shell is impacting HL tau. Here's the XZ tau Outflow, I am not sure how this outflow relates to the shell, okay? But people have seen it with ALMA, and this is a paper by, study by Yen et al. 2019, where they show they detect the expanding bubble from XZ tau, and they actually say that it's not that this bubble can affect the mass loss rate, the mass inflow rate from the envelope of HL tau into HL tau. So instead of you probably think of outflows of possibly triggering star formation due to compressing dense gas and triggering stars formation. That's people have talked about that. I don't think there has been any observational evidence for that. But in this case, the wind from XZ tau it's doing the opposite. It could be affecting the mass inflow rate from the envelope from HL tau into HL tau, and actually, if it weren't there, the HL tau system would probably get more mass. So that's another possible effect of outflows on the star formation process. So other people have looked at other star forming regions. Low mass star forming regions, and I say low mass star forming region even though I have Orion A here, because the most of the shells that were seen in this study are in the regions where low mass stars form in Orion, and there was also a survey in Taurus which found other shells. They do provide internal energy for the cloud, enough to feed the turbulence. However, there's not enough momentum to disperse the entire molecular cloud complex. So they can only disperse about 10 to 15% of the gas. They can create cavities, local cavities, but it doesn't seem to be similar to outflows. It doesn't need to be the feedback mechanism that can disperse the entire star forming region. So other mechanisms are needed. What it is interesting is that it looks like the mass loss rate that is needed in order to drive this shells is about 10 to the minus 8 to 10 to the minus 6 solar masses per year. A little higher compared to what people measure in T-Tauri stars, but this could be the higher end tail of a distribution of mass loss rates in young stars. So that's worth further investigating, how these shells form and which sources can create them. So that's what outflows and winds from young stars can do in the cloud and clump scales. Let's take a look at then what they can do in core and envelope scales. And I concentrate on this because, well, for the rest of the talk, because it looks like outflows might have the most impact at the scales. They can perturb, as we've seen from previous talks, outflows form very close to the star disk system. And so as they move out and puncture through the envelope and core, they definitely have to interact with it, and they could perturb it. They should certainly perturb it. The envelope and core are the main mass reservoir of the forming star. And so the outflow, as it punctures through, can perturb it and affect the mass assembling process. It has been seen that as Tyler already showed you the first day, that the opening angle of outflows is seen to widen as the protostars evolve. This has been seen both in interferometric studies as well as infrared studies showing the nebula, the scattered nebula around the young stars. There's a recent paper by Abel and Tom McGath and collaborators, which show that they don't see any actual opening widening of the opening angle as these stars evolve. So you might want to take a look at that. But I think that in order to study this, the impact of outflows on the envelope, one really needs interferometric studies, and not the interferometric studies of the past, but those of the present and the future, as I'll talk in a minute. But before that, I want to also mention that simulations also show that outflows can have an impact on the surrounding. Here's a hydrodynamical simulation back from 2014, but MHE simulations show similar things. I'm showing this because it's the one that I think has the nicer movies, but you can see that an outflow is formed around, here's the age, around 0.18 million years. We have let me go back. We have a core with some turbulence, gravity, it collapses, forms a star, which drives an outflow, and the outflow disperses the gas. And by the end of the simulation, you have a star that is only 40%, has a mass that is 40% of the mass that which you started with. So as has been mentioned in other studies, it could be that outflows are the main source of that star formation efficiency in cores, which has been said to be around 40 to 30%. This particular simulation shows that it's 40%. And so in order to study that observationally, I think it's important to not only map the outflow with the interferometers to look at the nice details like those studies that I quoted here, but also to study the core. And in order to do that, you need to probe the small scales as well as the large scales. And usually when you think of Lee, you don't think of interferometric studies in the millimeter, but I think it has this paper has a very nice sentence at the end of the abstract. It says, our results demonstrate the importance of including low spatial frequency emission for the interpretation of interferometric maps. And I think this cannot be stressed enough, especially if you want to be probing the gas at different scales, both the outflow and the environment. And here's a visual example of this. Here's HH46 as mapped by the 12-meter array from ALMA observations, cycle 1 observations in CO. Here's the 7-meter array, which has a lower resolution, so a more compact array. Here is what you get when you add the 12-meter and the 7-meter array data. And it's not until you add the total power antennas is that you get the full picture of the outflow as well as the cloud in green, as you can see in green. And also, you cannot probe everything in the outflow. There's some extended emission inside the outflow cavity that is not that is lost is filtered out in the interferometer only data. So in order to probe the impact of outflows on the surrounding, one needs total power that is to trace the large scale emission. And so that's what we did when we set out with this cycle 6 data project, and to study a survey of different protostars at different evolutionary stages, class 0, class 1 flat. And you can see here the red is redshifted outflow, blue is redshifted CO, and the green is C18O, tracing the envelope. This is work that is, this is all thanks to the major work by Chenghan Xie, who will be talking about this and more after me. But this is his most of his thesis work here. You can see that the class 1s are more collimated. Class 1s have a larger opening angle, and by the time you get to the flat class, you see much wider opening angles. the nice thing about ALMA is that it has the sensitivity and not only the resolution, but the sensitivity to detect the C18O through 1 and 13CO in outflow in 13CO and C18O. That's very dense gas that is being that is outflowing. So here, this is the normal 12CO outflow in blue and red, and the C18O envelope. But here you can see outflow, the C18O outflow in blue and red, and this is the envelope in green emission. So let me skip that. Well, we see the outflow impacting the envelope in C18O and 13CO. And we also see very wide opening angles in this class flat source with almost, let's see, I don't know what the opening angle is this, but it looks like it's a very expanding shell, parabolic shell that is impacting the surrounding envelope as traced in the C18O. So we see that outflows widen with time and with this data as well. You know, here's showing an example of the different classes. Class 0, very collimated. Class 1, opening angle, it's larger. Class flat, even wider. And maybe what we're seeing in exit tau is
Hector, 5 minutes.
Yes.
Thanks.
Okay, you're almost done. Yeah. It's an extension of this progression of widening angles. Why this is important at late stages? We heard yesterday about possible late stage infill. So you know, you might think that the impact of outflows on the surrounding is only important for the earlier stage, but you know, if there's really late stage infill, then we need to you know, see what the impact of the outflow could be on that late stage infill. Well, opening angles, you know, it's all old news, I guess. The classical opening angles. So we can actually get maps that are of the momentum and energy, and we see that the momentum distribution and the energy distribution of the outflow is also opening as the protostars evolve. And here's our plots of that. You can see momentum opening angle increase as well as energy opening angle, and I think Shenghan will be talking about that as well. We can see what the distribution, the angular distribution of the momentum and energy is, and you can see how much more collimated the class zeros are in terms of momentum and energy. I should, well, probably Shenghan will say that. I'll just skip that. Why is that important? Why is this important? Well, this is, you know, like I said, measuring the opening angle is nice and well, but you know, if we want to see what the impact of the outflow is on the surroundings envelope, we need to take a look at what the impact of what is the momentum and the energy that has been injected towards the envelope. And these are models that Lee was involved in of outflows interacting with the infalling envelope. And again, we need this kind of data that proves not only the outflow and but also the envelope to try to see what the interaction between the outflow and the inflow is. We were able to determine, or these are preliminary results, showing that the average mass loss rate by the end of the protostellar stage is about 3 to 6 solar masses. That's quite high, which means that, you know, outflows can have an impact on the core and probably the star formation efficiency. We're looking into that into more details. As a last thing, I want to say that Lee has also, you know, I did find this paper where Lee has was involved in looking at molecular outflows. There has been a renewed interest in looking at molecular outflows from F-Urani stars, and Agnes already talked about this. So this is from Apex and from ALMA observations. And this is particular interesting. This is from the Lucas Chiesa group in Chile. They were originally using this ALMA data to study the disk in F-Urani objects, but in the end, they got very interesting data from the outflows, and they published this in a series of at least 4 papers, I believe, different sources. To end with, I didn't know where else to put Lee's famous figures, so I decided to show you this. This is an interesting source, not very much on it in the literature. It's called the ARO 4249 source, HVC, also HVC 491 or HOPS 134. You can see it here very nicely in HJ and K, and also in SCSS. This is in galactic coordinates. You can see very nicely that it in CO, it looks very similar to the optical or near infrared nebulosity, and also it looks very similar to that figure from Lee, but with the arrows pointing in the different direction. So here's that's the only place I could find to put Lee's figure. So thank you, Lee, for all your work, and I'll leave my summary here for you to read, and I'll take questions. Thank you.
Okay, thank you very much, Hector. Questions?
Hi, Hector. This is Enrique.
Hey.
Very interesting talk. Thank you. I would like to offer like a complementary point of view to your discussion, because it was very clear that outflows do not seem capable of dispersing the entire clouds. But so in our picture, it is likely that clouds do not need to be dispersed by the time they're forming low mass stars. So according to what I said on Monday, the clouds evolve by accretion, they accumulate more mass. And so after a few million years, say 5 or so, they become massive star forming regions. And then at that time, it is the UV from the massive stars that it becomes able to disrupt the entire cloud. Of course, the outflows may be capable still of, reducing the star formation efficiency before that. But like I also mentioned, because the clouds may be accreting from their environment, then the observed star formation efficiency never gets very large, because like I said, the gas mass seems to be, according to the simulations, seems to be increasing faster than the stellar content. And so they always seem to have a low star formation efficiency, even if they're forming stars as fast as they can until they get destroyed. So, but I mentioned efficiencies of maybe 5%. So maybe we didn't include outflows, we just included UV feedback. So perhaps with the outflows, you can reduce that to the canonical 2 or so %. So, but our claim would be you don't really need to destroy the low mass star forming clouds until they become high mass star forming clouds.
Okay, so in this picture, you think that Taurus, for example, would become a high mass star forming cloud eventually?
In principle, yes, although I don't know if Taurus is the best example, because it seems to be like a particularly highly magnetized cloud and quite above the midplane. But other low mass star forming clouds, yeah, in principle, after several mega years, they could become massive star forming regions. Yeah. One thing to take into account in order to try to test this observationally would be to look at the atomic mass reservoir that the clouds have around them, to see if there is a possibility of them growing.
Okay, good. Another feedback source that I forgot to mention is that it could be nearby high mass stars, which more people are finding thanks to Gaia, for example, or parallax studies, where you can actually see that there are certain. You can take a look at the distance of the clouds with respect to different kinds of stars.
So there's some questions on Zoom from Tom. He had his hand raised first. If you want to unmute yourself.
Hi, Hector. Do you hear me?
Yes.
Yeah, okay. Hey, and it was a beautiful talk. But I'm going to quibble a little bit with your take, as you might guess, on the Hable et al. Paper, where we used HST scattered light observations.
Yeah.
And the main conclusion of that paper was that there was no growth through the class 1 stage. So we didn't really detect class zeros. And so I think there's strong evidence that's emerged that there's a growth between the class 0 and the class 1s. But we found that during the class 1 phase that there didn't seem to be any growth. And on top of that, we found class 1 objects where most of the envelope had been accreted. But the outflow cavities were fairly narrow. For example, there were only like 8 degrees or so. So they could not have been cleared by the outflow itself. And then when you get to the flat spectrum sources, we couldn't really detect the cavities again. And we think in many cases of those, really the envelope is gone and there's just dense cloud surrounding it. And so you have a disk with a dense cloud and maybe some sort of infall, but the core has been dispersed. And so I guess what I'm asking is, could you from your data see a picture where there's a growth from the class 0 to class 1? After that, there's not really a significant growth, and potentially the dispersal of the envelope isn't really due to the growing outflow cavity, but instead is maybe most of it's eaten up or something. And then you hit the flat spectrums phase, and now the envelope is gone, and you have a wind just sort of propagating into the cloud. Would you consider that sort of a potential reasonable picture with the data you have?
Let's see. It's a possibility, but we are currently studying the core. We don't have the preliminary results on the cores. We've been focusing on Shanghai has been focusing on the outflow. So that is to come. But I mean, if I take a look, if I use the C18O as a probe of the envelope, I can see that, it looks like the outflow is clearing up the surrounding. I mean, it's true that by class flat, you don't see, there's many sources don't have that much envelope surrounding it, but the ones that do seem like they are interacting, or the outflow is interacting with the surrounding envelope. So.
Yeah, I mean, we find that for the flat spectrum sources in general, and there's exceptions to that the disk masses exceed the envelope masses in the dust continuum. So that in many cases, the dust is basically, the envelope is basically gone. And so I guess the other question is, do you see growth through the class 1, but maybe you don't have enough data to see that?
No, this is why we need, No, we don't have, I mean, this we targeted 7, I'm only showing 6, 7 per class. We need more. That's why we want to do this large armor project. But yeah, we certainly need more to be able to see if there's any evolution within classes.
Yeah. Okay.
But let me, okay, sorry, go ahead.
No, I was going to say, normally we say you can take the conversation offline. In this case, take the conversation online through Slack.
Okay.
Yeah. Okay. Thank you very much, Hector. It's generated questions on Zoom as well, and more from the audience here. But I think we need to move on, and at least we're moving on to a related topic. So, which I'm sure will generate more questions. So our next. Thank you very much, Hector.
Thank you.
So our next talk is by Chenghan Shit, and it's on the evolution of protostellar outflows and molecular bullets in Orion A. Thanks.
Hello. Okay. Star formation is a multi-scale problem, from molecular clouds to filaments to small disk. And protostellar outflow is the one that links all the scales. So I will start my talk with the take-home message. Okay, so we accurately measure the outflow mass, momentum, and energy ejection rate. And we show that looking at momentum and energy ejection rate maps is a powerful way to find jets and bullets. And we can use protostellar jet mass loss rate to measure protostars accretion rate. So that's the take-home message for my talk. So why is it important to look at outflows? Because it can possibly explain the difference between IMF and CMF, core mass function, and protostellar outflows is a source to sustain turbulence in a cloud. And also it reduced the star forming efficiencies for the gas accretes onto the protostars. So the recent Van Daan survey done by Tobin et al. 2020, they look at 328 protostars in Orion molecular clouds with ALMA. And one surprising result is that they found the disk radii decreases as the protostars evolve. And this is at odds with the MHD simulations which predict disk growth. So the authors propose that this is due to the protostellar outflows removing a significant amount of gas, preventing the accretion of the high angular momentum materials and thus limiting the disk growth. So if we look at the disk formation, it is top down. So the large scale processes such as the collapse of the protostellar core determines the evolution of the total mass and angular momentum for the protostar disk system. So on the right-hand side shows a recent simulation by the Princeton group. So they look at the angular momentum flux through a 20 AU sphere. And they found the angular momentum is dominated by larger scales, larger scale inflow. So if we look at the removal of the mass and angular momentum in disk, outflows can remove a significant amount of mass and angular momentum. It has been found in observation as well as simulation. But there's some caveats. So for observation, the mass loss rate by outflows is very uncertain. And as for simulations, it depends on the magnetic diffusivity parameter. So, to understand the role of outflows playing in removal of the mass and angular momentum in disk, one needs to establish an accurate way to measure mass loss rate by outflows. So we use ALMA to observe 21 sources in Orion A. So the blue and red shows the blue shifted and red shifted CO outflow, and the green is C18O tracing the core. So the first row represents class 0, and second row class 1, and third row flat spectrum sources. So which is more evolved class 1. So it's aligned in terms of bolometric temperature. So you can see as the outflow evolves, the outflow cavities widens over time. So we did the inclination correction. We've used Tobin's Van Daan survey, disk continuum, high resolution ALMA observation, just look at using the major to minor axis ratio to derive the inclination angle. It is important to point out without the inclination correction, the outflow mass loss rate can be changed by a factor of 3 to 5. And without that correction, any evolutionary trend can be easily wiped out, especially for small samples. So as for the distance to each protostars are from Gaia, derived by Tobin et al. 2020. So if we look at the recent large surveys, we start to find a lot of like conflicting results. There's the Apex results surveying 54 outflow sources, and they found the outflow mass momentum injection rate decrease between class 0 and 1. On the other hand, you also have large surveys of 45 protostellar outflows by Frederickson et al. 2020, and showing that the outflow mass and momentum ejection rate is independent with evolutionary stages. So we're getting conflicting results. So the question is like, why? Why are the mass and momentum ejection rate scattered all over the place, even with large samples? So I think the main reason is the method used to derive the mass and momentum ejection rate. So usually how this is derived is people just simply measure the outflow length and divide by the outflow characteristic velocity to estimate the outflow timescale. And they measure the mass of the outflow, divide by that timescale, and that gives you the outflow mass ejection rate. However, that has a lot of assumptions. So this is basically assuming that the molecular gas inside the outflow moves from the source to the current position in a uniform velocity. So this is a very bad assumption, because what we see, the most of the gas do not move from the source. They are entrained gas. They get pushed by the high velocity jet. So they're not directly ejected from the central disk. And also they're definitely not moving in the uniform velocity. It is very difficult try to selecting the outflow length, because as you can see, it can be easily cut off by the field of view. And also choosing one characteristic velocity to represent the whole outflow, it's also very problematic. So we use a modified version method first used by Bothams et al. 1996 to obtain the mass ejection rate. So the idea is to create ring mask. So we measure the mass spectrum within the ring mask and the outflow mask. And for each velocity channel, we use the width of the ring divided by the velocity channel relatively to the system velocity. That will give you the crossing time across the ring. So we can do this for each velocity channel. So for each velocity channel, you have a different crossing time. So by adding up everything and use the mass spectrum divided over the crossing time will give you the outflow mass ejection rate without any dependence on the choosing the outflow length and also the outflow velocity. We can also vary the different ring size to get the mass ejection rate profiles. So this is the average over class 0, class 1, and flex spectrum sources. We find class 1 has higher mass ejection rate compared to class 0 and flex spectrum sources. So by adopting the duration from Daham et al. 2015, we found around 3 to 6 solar mass is removed by the outflows at the end of class flat. So the numbers are very high. This is suggesting the mass is replenished from the surroundings. So we can do one step further. So we can apply it on every single pixels. So this idea has been done in simulations, for example. So instead of creating rings, we can obtain the mass spectrum for each individual pixel. And for each pixel, we can compute the crossing time across the pixel. So this is like flux tracing. So by doing this, we can create the first instantaneous mass, momentum, energy ejection rate maps. So here are some results. So from these mass, momentum, energy ejection rate maps, we start to find a lot of high velocity jets. A lot of high velocity jets starts to pop up in momentum maps and also energy ejection rate maps, for example. So here are just some examples for for high velocity jets. So this so we start to see so these are energy ejection rate maps. We start to see a lot of molecular bullets popping up in energy ejection rate maps. If we just look at the intensity channel maps, it's very hard to see those. So this is something very interesting. And for some sources, we see the bullets are tilted. For example, HOPS 169, which is indicating there's a precession. For HOPS 355, we can see that there's like S shape. So there's a precession going on. So we detected 6 molecular jets in class 0. Excluding the HOPS 408, which is a point source. The detection rate is 100%. Even though it's a small statistics, this indicates most, if not all, class 0 sources have molecular jets. And from the review paper of Bailey 2016, we see a lot of more evolved class 1 and class 2 jets are mostly detected in atomic and ion lines tracers such as O2, H alpha, and S2. So this is an emerging picture showing that there's an evolution in the gas content in the high velocity jets from molecular to atomic. So we can also look at the energy per pixel along the outflow axis. So each peaks corresponds to the position of the bullets. So we can measure the bullet period, which represents the period of the impulse enhancement in the mass ejection from the innermost region of the circumstellar disk. So we measured the bullet periods for different class 0 sources. So these are derived from momentum maps and energy maps. So we see there's a tentative increasing trend in the jet bullet period. And by looking at the momentum and energy ejection rate maps, we see the same trend. So with 6 sources, the data reveals a tentative increasing trend for jet bullets period. And the caveat is that we cannot clearly constrain the slope for the evolution of jet period because there's not enough sources. So this is something very interesting because the period of these bullets are around 100 years, which is correspond to disk scales. And it has something to do with accretion. So we look into, we identify the local peaks of the bullet and fit to the Gaussians. So from HOPS 10, we can see the energy ejection rate for each bullet, and we plot against the distance. So this is around like 300 years time scale. And we can see there's like sudden bump that's correspond to episodic accretion. And we can see the general trend of the energy ejection rate going down. So if we plot all the bullets against the bolometric luminosity, we can see there's quite a lot of scatter. So this is telling us that there's a large change in accretion over the time scale around like 200 or 300 years. So the bolometric luminosity corresponds to the most current accretion. So we want to plot the bullet that is closest to the protostar. So if we do that, we plot the HOPS 10, 11, 169, 355, and 198, and we can see it shows a very beautiful linear line. And we also plot the other literature results, which is lower than our slope because they use the outflow length divided by the outflow velocity, which underestimate the outflow mass ejection rate. So this is very remarkable because it shows a linear relationship. So bolometric luminosity should be proportional to accretion rate. In class 0, the accretion bolometric luminosity is roughly equals the accretion luminosity, which is proportional to accretion rate. And we're plotting against the mass ejection rate, and it shows a one-to-one relationship. So this is showing that we can use protostellar jet mass loss rate to measure a protostar's accretion rate. And this has been shown for working for T-Tauri stars. And this is from Qinfei Li's review paper. They show there's a strong link between mass loss rate and accretion rate. And also they show there's possibly a different slope for class 0 and class 1 sources. So, so this is something very interesting. We found at the end of class flat, around 3 to 6 solar mass are removed from the source. This is telling us there's possibly a continuous accretion towards the core. And also we find a tentative increased trend for protostellar jet period in class 0. And at last, we found a strong linear relationship with bolometric luminosity versus the protostellar jet mass loss rate. So this indicates there's a one-to-one relationship exists between the accretion rate and the jet mass loss rate. So this is very important because for class 0 sources, it's very embedded. It's hard to see H alpha and other commonly used tracers. So if we can, and also it's difficult to even using CO tracers because it's very embedded and it requires high angular resolution. So if we can use protostellar jet to trace the accretion rate, this will be very, very interesting. So that's the end of my talk, and I will take questions. Thank you.
Thank you. Okay, we've questions. Well, question from the audience.
So you showed those various histograms, class 0, class 1, mass loss rates, and I think you said like halfway through that the class 1 mass loss rates were higher than the class 0. But how does that match with your fourth conclusion here that there's a higher, that they're correlated, right? The mass loss rate and the accretion rates are correlated. I would expect the accretion rates to be much higher in the class 0 phase. Is it just that you're talking about jets here, but broader outflows earlier?
Yes.
Okay.
Yeah, so one of them is, so the connection between accretion rate and is the jet mass loss rate, and the other one is to the general, the wider outflow. So if I see if I can, okay, so these are the momentum rate and energy ejection rate angular profile. You can see for class 0, even though it's very high, but it's very directional. And as you go to class 1, it becomes very isotropic. And if you go to flat spectrum sources, it's almost at 1 order of magnitude smaller. So
does this imply that the outflow rate, if you just measure the mass loss rate in a class 0 outflow, that's a better tracer of the accretion rate than for a class 1?
So in class 1, we don't really see we don't see molecular jets. So we're talking for molecular jet, we're talking for class 0 only.
Okay, there's a question from Patrick.
Yeah, nice talk. Can you estimate the ratio of the energy carried out in the jet and the accretion luminosity? What fraction of the energy that is being, I mean, if due to gravity, is radiated away in the jet?
So we don't know the accretion luminosity. So but we do know the for the energy of the jet in class 0 is very high compared to the wide angle wind. So
you have the accretion rate, and with some stellar modeling, you know the radius of the star, so you can, it's not a measure, but you can make a reasonable guess for the total energy which is radiated away by gravity. So it would be very nice to have, if you can have some ratio between the total energy carried out by the jet and the energy which is due to gravity.
Yeah, we haven't looked into that, but that's something we'll look into in the future. Yeah.
Okay, well, let's thank Shenghan again for a really excellent talk. We now have a short contribution from Hans Zinniger online. Hans, do you want to unmute yourself?
Thank you very much. Okay, so am I the only one to give an extra speech, or are there other people?
You're the only one to give a 2-minute speech, Hans.
Okay, then it can be 3 minutes. Okay. Let me start by saying what a wonderful conference this has been. Lee, of course, is always good to trigger a good discussion and event. Perhaps Lee should have the honor to suggest the next Star Formation Fest. I would also like to take this opportunity to thank Tom Ray and his Diaz team for organizing this hybrid event in such challenging times. I perhaps actually played a small role to entice Tom. In my few minutes here, I have 3 thoughts to offer, and maybe a final scientific historical question to Lee. My first thought is about what's in a name. Hartmann, with a double N. That, to me, points to German ancestors. And perhaps Lee can enlighten us about his family history and what led him to become a scientist and astronomer. This is always interesting to know. Moreover, I wonder whether it hit you that there are actually several other astronomers with the name Hartmann. Hartmann seems to be a good name to be an astronomer. The most historic one was Johannes Hartmann, who in 1904 discovered the stationary calcium H and K lines, aided by spectroscopy of spectroscopic binary star, Delta Ori, to discover the presence of the interstellar medium. So Hartmann really goes back to the origins of our field of star formation and the interstellar medium. The other Hartmann that comes to my mind is William Hartmann from Arizona, who was a planetary scientist and an artist. He wrote, and an author. He wrote 8 books. And yet another Hartmann is I forgot to mention that Hartmann, the astronomer Hartmann from 1904 from Potsdam, actually also created the test for wavefronts. So the famous system, wavefront testing system, the Scheck-Hartmann sensor is related also to that particular Hartmann. So Hartmann not only in terms of theory but also in terms of technology and in instrumentation. And the last Hartmann that comes to my mind is actually Dieter Hartmann from Clemson University, who is a high energy astronomer, astronomer of radioactivity. So I wonder whether you made the connection that the Hartmann is actually a very good name to be an astronomer and a very good astronomer. My second thought goes to what I would call the Hartmann-Calvet couple. Let me see whether I can find my notes, what I have to say here. Yeah. So,
can I tell you, Hans, that Lee, well, not just Lee, but Nuri are waving their hands here.
Yeah, it's good. So I wonder how much Nuria contributed to Lee's success. I suggest we should give a warm applause, not only for Lee and his great achievements, but also to Nuria for her role in this super successful team and couple.
Okay.
So for every successful man, they say there is a great woman behind him. So that's my second thought. And it has been a pleasure, of course, to know them both. And I wish them that they keep going. My third thought goes to
This is the final thought, Hans.
Yeah, final thought.
Yeah,
final
yeah.
thought that when I went on my last official trip as a Sophia astronomer, my last colloquium, which was actually at University of Michigan. And that was when Lee was my host. And I remember he picked me up at the Bell Tower Hotel. Do you remember, Lee? Mira, I even have a flyer of the University of Michigan. And my last thought about the University of Michigan is that, to me, actually, that's my personal opinion, it's actually the top address of star formation research in the United States. After Lee and Nuria moved from Harvard to University of Michigan at Ann Arbor, joining Mike Meyer, Fred Adams, Ted Birkin, and several others, I think this has become a very powerful and shining example of an institute particularly dedicated to star and planet formation in the United States. And I wanted to end with a question for Lee. We had heard a lot about the FU Orionis phenomenon and Lee's fundamental contribution to the interpretation of that phenomenon due to disk instability. But there was a theory that preceded this idea, and I think it was George Herbig who was the proponent of that. So my question for Lee, maybe he can address it in his summary talk. How did he have actually a personal interaction with George Herbig to discuss the origin of the FU Orionis phenomenon? And with that, I will congratulate Lee and Nuria for their outstanding achievements in astronomy.
Thank you, Hans.
There are only two more couples in astronomy. This is Hartmann and Calvet, and then there is Elmer Green, Bruce and Debbie Elmer Green, and maybe you could mention Lada, Charlie Lada and Liz Lada, although they are not married. They're sisters.
Okay, so it's low number statistics, Hans. Don't deduce anything from it. Okay. Okay.
It's just
so
what comes to my mind.
Okay.
Let me address that at the end, Hans. Okay.
Yeah. Okay. So right. Well, thank you very much, Hans. And now, how shall I put it? We're leaving the best wine to last, and we have some of the oldest wine. Well, oldest and best, right? But it's going to be a double act. I don't know who's going to be the comedian in this, but so Javier is going to speak, I think, first, and then.
Okay, so thank you to everybody here for being here. This talk is supposed to be somehow what Lee have done regarding molecular class formation. So I have to warn you that it's strongly biased. So don't offend if you don't get cited or quoted. And well, the original name that I gave to the talk is a pictorial review on molecular cloud formation, but it could also be called How to Dance with Lee's Ideas on Cloud Formation and Evolution. So first of all, let me thank the log. I think that they have done a great job. Alessio, Pauline, Simon, Deb, and Camille. And of course, special thanks to Eileen, is over there. And of course, to our guide, our spiritual guide on this meeting. So I also want to thank to the ever rising hand, Hans Sineker, because he, as I told you yesterday, he has been somehow part of the idea of this meeting. And well, first of all, how did I meet Lee? So this is a personal story. So how did I meet Lee? Well, the guilty has been Paola D'Alessio. I was very much in love with her. And as you may notice, I have her at some point. And the thing is that Paola was a student of Nuria in Venezuela back in the early 90s or even before that. And you may be kind of feel that this picture looks familiar. And the reason is that they were kind of reproducing this other picture that it's famous from the Harvard ladies. No? So Nuria was working in Venezuela, in Mérida. Paola was also a student there. And of course, Nuria was with Lee. No? So at that time, Lee was really famous. He have explained, as Nuria told us, the line profiles of the T-Tauri stars. He has also been suggested that the disks must be flared because otherwise you won't explain the spectral energy distributions. And I met Lee finally back in '94 in a beautiful meeting in Cozumel. Unfortunately, I don't have pictures of that meeting, but I have pictures of a meeting a little bit later than that. I'm including now some pictures of people that you may know, although they are not here. For instance, Alex Raga, that was Alex Raga back then. Now he looks like that. This is Chema Torreyes. Now he looks like this. This is Susana Lizano, back then and now. These are Lee and Nuria. And for the people online, then I'm including a picture from yesterday, so it's quite updated. Bo Rayport was there also in that meeting. All the students were in love with Bo, were impressed by Bo. Luis Felipe Rodriguez. And well, myself and Paola. And well, unfortunately, Paola is not anymore here, neither my hair. So anyway, I was in love with Paola, and she was going to make a postdoc in Harvard with Lee and with Nuria. So at some point I said, well, she's leaving, so what will I do? So I spoke to Enrique and I told him, well, Enrique was my advisor. And I told Enrique, Paola is leaving, he's going there. And I think I'm going also with her. So better if we find a project or something to work with. So Enrique spoke to Alisa. He told her that maybe I could start working on comparing numerical simulations and observations. And Alisa agreed with that, although she had a baby, she had a newborn baby. So it was kind of difficult to find her, although we still made some work. But then, so we fly to Boston, of course. I had her, but also some kilos, some pounds. So, and there was this beautiful team in which Lee and Nuria were working. There is Paola, there is Cesar, there is James, Ray J, and they were always laughing all the time. Actually, Alisa, I believe Alisa at some point told them, what do you do every Thursday in the afternoon? Because it was really, really funny and nice working meetings. So some of you may have quoted Eric's papers. He had an important contribution, as we heard before, from Nuria, although he quit astronomy. This is Eric. This is James. James was always making faces to my pictures. And besides the faces that he was making, he somehow was estimating the accretion rates in intuitive stars. So, and the most impressive thing that I remembered from him is that he was always finding correlations of everything. So at the end, we call him Mr. Correlation. And there was, of course, Paola. Paola was working on the D'Alessio irradiated accretion disks models. Those also were influential papers that still are producing results. So at that time, Enrique and myself had this paper. It was one of the papers of my thesis, in which we suggested that molecular clouds should be formed by the compressions of the global either stellar and action of the feedback from the stars, but also from many other sources like spiral alarms and things like that. So we were making simulations on scales on 1 kiloparsecs, and we found that the clouds could be formed very fast by this global action of the stars. So turbulence on larger scales. So then it came the Stars and Planet meeting. I brought these results to that meeting. And at some point after the meeting, I saw Lee, I believe, it was still in the meeting in the elevator of the hotel. And he asked me, well, Javier, how was your poster at this meeting, no? And I told him, well, you know, I kind of felt that Bertoldi and Mackie didn't like it, no? So he was kind of impressed. So what happened? What was about your poster? So I told him, well, it was about molecular clouds being constructed fast and evolving fast. So he said, really? Is that so? And then he started making questions. How fast are your clouds being constructed? How fast they get destroyed? Could the whole process last like 5 or 10 million years or so? Would you show me some animations, and can we start discussing this? So, of course, the thing that Lee had in mind at that time is what Cesar already told us on Tuesday, I believe, that there was this pository problem in which there were no old stars associated to molecular clouds. So the stars, if you look at inside the cloud, then you have always young stars, and the old stars are already rid of the gas. There is no gas associated to that. So we started working hard, as you can see. I started entering into Lee's meetings and enjoying the laughing. And of course, Lee was doing his part. He was also inviting us and having fun. No? So at the end, we came with this paper in which we somehow were arguing that you already could form molecular clouds on large scales, on 30 parsec scales, and star formation could be triggered simultaneously just because of the action of either a passage of a spiral arm or the stellar action of the stars that have been already created before. So we also computed the scales, the time scales, and so on. No? And somehow this was the precursor of the other paper that has been quoted. At that time, Mordecai, Ralph, and Andy Burkert were also arguing that the turbulence was decaying fast. It could not be maintained over more than one free fall time or one crossing time. They were not the only ones. Also, Paolo Paduan and the group of Jim Stone and Ivo Stryker. At that time, Patrick was also contributing. He was proposing that if you have these compressions in the diffuse gas, then you can trigger thermal instability, and then that will help also to form molecular clouds. Fabian Heich, who also spoke here, was also contributing, arguing that indeed the turbulence has to be on very small scales to prevent collapse, and also that you require strong magnetic fields to avoid collapse. If it's a realistic magnetic field, then you don't prevent collapse. So then I came to make my postdoc to New York City with Mordecai, and I was interested in how turbulence could be transferred from the largest scales into the smaller scales to see if there were some kind of support or something like that, no? And we didn't find much about that, no? So turbulence was always dissipated. And by that time, we made this paper, the one that has been quoted here several times. I don't have a picture of Ted, Lee, and myself, but thanks to the technology, we can switch a little bit here. So these were the guys that made this paper. And the main result is that clouds could be formed by large-scale shocks. And as they become molecular, they also become gravitationally unstable and collapse. So that was the big result. Then at that time, Joao, while we were talking about a fast molecular cloud formation scenario, Joao and Charlie Lada were proposing that some clouds at least could be very static. They could be actually in equilibrium between thermal energy and gravity. So then we came with this other paper in which we were proposing that you could fit actually a von Neubert profile to clouds or to cores that are evolving fast, just because you are making averages. And then Lee came with this squared von Neubert sphere, or von Neubert squared, sorry, and he was saying, well, you know, it could be. But you actually can fit anything, no? So as soon as you make averages, then you smooth everything out, and it could be also a squared thing, no? Rectangle. A rectangle. Okay, sorry. So then Fabian and Enrique were making these models of molecular cloud formation by large-scale streams. So it was Patrick. So actually here Enrique is showing this convergence. I believe that the people that he's talking to is Chris McKee, and I still think that McKee still doesn't believe us. So anyway, the idea is here we have a animation by arrow, no? So it's not a real animation, it's a set of pictures in which you build up the cloud by these large scale flows. Here on the left, you have the diffuse medium in blue, then the dense medium in yellow and red. And here you see only the dense gas. So as time goes on, let's see, I don't know if it's evolving. It is? Okay. I don't see it here. So it's, okay, so the point is that as you accumulate mass and as thermal instability is triggered, then it becomes cool, it gets many Gibbs masses, and it collapses. And it collapses also not because of this accumulation, but because also it's collapsing laterally, and then it's getting more extinction, it's getting more mass, so it collapses. So, and the one key ingredient here is that as it collapses and as gravity takes over, then the gravity takes over the kinetic energy, and they follow a kind of virial relationship, even though it's not a virial equilibrium. So, but you can find these kind of results also in just pure embodied simulations. If you let go stellar cluster from cold conditions and let it collapse, after one freefall time, then you see that it reaches virial equilibrium. So a key point here is that virial balance, which is somehow observed in clouds, they could collapse, they will show virial type conditions after one freefall time. Okay, but then Fabian and Lee were making these pancakes, these sheets that were collapsing. Apparently they were pancakes, but although I guess probably they were also finding bagels due to this edge effect that Andy Burker was talking about a couple of days ago. Lee was also very interested in seeing whether these edge effects could also contribute to actual collapse, no? Just because gravitational focusing. And first, Lee and Andy were making these kind of structures in 2 dimensions, but also you can reproduce that in 3 dimensions without much difficulty. And at that time, I started to work with several people, of course, among them Lee. Some of them were kind of serious, like Adriana and Manuel. Some of them very nice people, like Fabian, and some of them a little bit more frenetic, as you can see in the pictures. So what we found in this series of papers is, first of all, that the column density PDFs, they evolved from being kind of log normal in the high mass end or in the high density end towards a power law regime, which was also somehow already observed by Jouni Kainulainen a few years before. So we also showed that the Larson relation, the column density being constant, is just an artifact of the definition of clouds, because we set a column density threshold to define clouds, and then you get, for all the clouds, you get the same column density, even if they have different shapes of the column density PDF. For instance, if you take a different threshold, then you get a different power law, but you get a power law, a very good power law actually. But that's just a definition, a matter of the definition, and the fact that the column density PDF decays very rapidly. We also were finding that there is not a single velocity dispersion relation. If you put together all the data that is available, you find kind of a cloud. There may be some tendency toward larger velocity dispersions at larger sizes, but still a lot of scatter. And you can show that this scatter could be interpreted in terms of the column density. And actually, if you look for high column density guys, they will be located typically over here, and low column density guys over here. So that may be also talking about some evolution. And all this can be explained in terms of what we call the Hector diagram, or the Larson ratio against column density diagram, in which the column density is not anymore constant, as Larson proposed, but there is a big range of column densities. And you can see that all the clouds more or less are located along some sort of virial equilibrium, although typically, or sometimes, or many times, a little bit above that. So anyway, then Lee also had the idea of working on the IMF. And we try to understand something that Hans Zinecker, and that's why I put the rising hand there. Hans Zinecker had proposed before. And the idea is that gravity can produce a slope of -1. So I'm not going to enter into many details, but Lee tried that in 2010 with Tina Su and other collaborators. And they were showing that you can, as accretion goes on, the IMF or the mass function of the seeds that you put in your simulations evolve towards a slope of -1. We were showing also that this could be happen in isothermal simulations that are collapsing in 3D with different Mach numbers as long as they are somehow subvarial. But also, I think a very important result is that you can reproduce also this in M-body, without any thermal physics. So just pure M-body, and you count clusters, you count groups, and then you develop a slope of -1. So the idea of Lee is that this gravity builds up this slope of -1, but it's an asymptotic result. So it may be that as soon as you stop accreting because feedback, then it stops a little bit earlier, and that may define the IMF. So Lee has several ideas, and some of them look a little bit magic at the beginning. No, I know that I've been making him work extra time sometimes, no? Sometimes in the morning, sometimes too early in the morning, even during the pandemic. Sometimes my ideas are not very interested, and they look like not such a good ideas, but we have been having great time together, and not only we, also other people. There is Maite. There is Lori Allen also in that picture, Kathy. So we have been having a great time. This is Lee's group. But also I have to say that it's been really personal, very familiar. They have been really like a family, no? Lee and Nuria. So they have been with us for quite a long time. It's been like almost 30 years long. They have been very supportive all this time. And well, let me finish those just recounting or trying to put few ideas that were before and afterwards the Lee. Before and after, before 30 years ago and now. No? So first of all, well, this idea that the disks must be like this, and how much we have evolved on time. So these look like pretty much the same, no? Well, probably I'm a little bit mean with that picture, but you know. We heard from Nuria that Herbig was complaining about this and about the Orionis, and actually, so we haven't seen those at that time. Also, at first, the disks were kind of flat, and then Lee proposed that they should be flared, and then all this idea that there should be a wind, there should be an enfolding envelope, and so on. No? So the picture is a little bit more general. So regarding the clouds, this was the former idea when I started studying, that the clouds were magnetized, they were in hydrostatic equilibrium or magneto-hydrostatic equilibrium, they should have to evolve the slope. Then we were proposing that clouds should be much more turbulent. And I think that this also has been confirmed by observations, where you can see that the old stars are far away and the young stars are right there, and there is a gradient in ages all the way down to the molecular clouds. So of course, now there you can find beautiful simulations with lots of physics and things, but I think that the idea is pretty much the same. You have collapsing clouds that, and somehow the feedback is trying to prevent or avoid to some extent the collapse. This was the picture of Orion some years ago, or many years ago. And now we have these beautiful images by Tom Megueth, in which you can find also the cores, the clusters. This picture was is shown in Lin and Lee paper 98. It's just the density of the young stars. Now we have this more complete picture of the cluster, in which also you can find that there is some age segregation, and always Lee is saying, you know, you cannot produce this with a turbulent box that is evolving over 10 free-fall times or more. You have to have collapse within one free-fall time or few free-fall times, and then you get this age segregation between the stars. This is from the work that Andrea, my student, is doing. This is the work by Tom a few years ago. So since Andrea didn't show her result because she wanted you to go to your poster, but we have people online that couldn't see the poster. So this is her result. Her result shows that the velocity dispersion of the stars in the ONC has constant velocity dispersion. So that suggests that it was formed within a one free-fall time. It just collapsed, no turbulence. We knew also that the Gould belts was this kind of ring having young regions, young star-forming regions. We now know from Marina that there could be kind of two different bubbles. Although that's disputed somehow by Joao, they argue that there is another bubble in Perseus. I'm not sure that he showed that, but that's a result from their team that involves Taurus and Perseus. But Joao tends to favor this other picture in which the Gould belt is just a projection of something that could be a spiral arm. So we don't know exactly how the solar neighborhood is right now, but it's been evolving the picture along all these days. Regarding the clump mass function, well, we have been told 20 years ago that it has a salpeter kind of slope, but now with the ALMA IMF, it seems to be a little bit flatter. So, and actually consistent somehow with a slope of -1, which will tend to favor Lee's idea. Regarding the IMF, well, this is the idea. There is the idea that gravity gives you asymptotically the high mass center slope of -1, and Patrick has shown us that probably or likely the peak of the IMF is due to these tidal interactions between the protostars and, of course, the thermal physics that involves the Larson core. And well, finally, how Lee has evolved through the time. So finally, thank you, Lee, for all these years. It's been great. It's been great being your friend and somehow your family. Thank you.
Thank you, Javier, for that pictorial trip through history. I don't know whether we can follow that with any questions, or really we should let the no hands. Okay, well, thank you again. That was excellent, and gravity lessons. So I think we have to follow up to this, Lee. Thank you.
Well, that's a hard act to follow. I'll try and keep this short because I know everybody's exhausted. It's been great being here. I've had a really enjoyable experience. It's a special experience. I thank Tom, the organizing committee, Eileen, everybody who worked on this. So when you get to a point like this, there's a logical, perhaps musical question you could ask, well, how did I get here? And I'm not entirely sure after all these years, but certainly a lot of it had to do with people that I worked with. And that was the major thing. I mean, what I realized early was that if you worked with people who are smarter than you are and more capable, that you could do a lot more stuff that you wouldn't be able to do otherwise. And so here's a list of people, my collaborators. Of course, Scott Kenyon was one of the, probably extremely important, John Stauffer, others, Javier, of course. And then I would actually put people in that, at least in the case of Duria, people who actually added me to their collaborations with Paola and also Tom McGath. And I don't mean to be downbeat, but I think I should just mention that both John and Paola have passed on. Which is sad for me, but also sad for the field. I've had a wonderful set of students and postdocs. And, when I think about this, one of the most important people in a way was Andrea Dupree, who brought me to the Center for Astrophysics. Because the number of people there, the range of opportunities, the range of people that you could interact with was enormous. And I don't think I would have had anywhere near this kind of career without that kind of opportunity that Andrea gave me by bringing me there and then paying me as an IUE postdoc for many years. So this isn't a complete list of folks, but it's, it just gives you an idea of the importance of working with great people. So I'm not going to try your patience, I hope. Just a couple of science points. I've been motivated for the last, well, I can't remember, but about the importance of gravity in star formation. The general idea that you have turbulence, which creates structure, and then, then really gravity takes over. Gravity is a long-range force, so you can't really get away from it. And Javier mentioned this result of the of the power law distribution. This is not an IMF model, as Patrick says accurately, but I think it's worth trying to at least understand part of it if we can. And the point that I want to make here, and this goes back to something that Hans did an indefinite number of years ago, sorry, there's a complication here. I'm not going to go into it now. These slides will go online, yes? Or so if you're bored, you can take a look at them. The point that I want to make here is that there have to be two processes, as Patrick said. There's like the fragmentation on the small masses, but I think you can grow to larger masses. And whether or not you get all the way to a -1 slope, as Hans argued in his paper, depends on how far you grow from the initial fragmentation mass. Okay, I mean, if you don't grow anywhere, then you just get your initial result. But if you keep going, you can make it more and more of a flat spectrum. And I think that really the difference between -1 and the saltpeter -1.3 is just that you don't, in the stellar case, you don't get arbitrarily far averaged over a bunch of star forming regions from the original fragmentation mass. And I think you can see this because you actually get the same mass function, -1 power law for young clusters. I think it's the same aspect. It's focusing, gravitational focusing. It's the cluster version of what Ian Bonnell and his collaborators talked about as competitive accretion. But here we don't have a fragmentation mass. We don't have a thermal mass. And so just as in Javier's simulation, where we just made it isothermal, so it was just limited by numerical resolution, here, you don't have the, if I can do, I don't know if this is going to work. You don't have like a broad peak here that you have to grow past. And so you can really see the power law just in the cluster mass function. We showed that with stuff with Alexandra and Andy. A little bit of history, if I can. So my first AAS meeting, my first American Astronomical Society meeting was in Chicago in, must have been, I guess, 76 or maybe 74, probably, must have been 75. And the Russell lecturer was Herbig, and he gave this wonderful talk on eruptive phenomena. And I thought this was great. I didn't know what to do with it. And then some years later, when Scott Kenyon came to CFA, I said, well, you know, he gave a talk on novae, and I said, well, maybe this is a nova. And he said, no, I don't think so, but I think it's what's called a dwarf nova, which is actually a thing where you've got a white dwarf and a companion star feeding the white disk around the white dwarf, and this disk goes periodically into outbursts. A lot of our ideas about accretion disks come from the early days when people were doing X-ray binaries. People like Jim Pringle and so on. So anyway, so this was great. So we did this stuff. And one of the things that I think really nailed it was when Scott and I went to Kitt Peak and used the 4-meter Fourier transform spectrometer to take these beautiful CO spectra. This took forever because it's effectively a scanner. And the interesting part about this was when we did the Cygnus objects, because this spectrometer was so slow, they didn't have a good guide camera. And so we were actually guiding on nothing. There was a voltmeter. And so we would just, with the hand pedal, would spend hours peeking up on the voltmeter to try and maximize the signal and hoping that we were getting something through it. Anyway, we did get that. We did the differential rotation that Lynn showed. And so, you know, that's the nicest, most complete spectrum of an astrophysical accretion disk that I think exists. And unlike the high energy versions of it, we've got tons of lines and tons of spectral features and tons of things to look at. And so it gives people like Lynn an opportunity to say, well, this doesn't quite work here, or you screwed up that part. But if you actually look at what a magnetorotational unstable disk looks like, this is what it looks like. This is a calculation from Shawan, an Athena ideal MHD, and it's turbulent. It's a mess. It's got a wind and it's got all kinds of ejection. So you have the general features of a steady, simple disk, but you've got turbulence and you've got some mess. And unfortunately, as of yet, nobody's taken the simulation and actually calculated observables, spectra, fluctuations in the total brightness. It's not a trivial thing to do, but it's something that really would be worth doing. And we have such a huge database of observations that we can really do a little bit about the physics of what an actual MRI accretion disk would look like. Forget that it's a pre-made sequence object. I'll just say one thing that I'm also kind of proud of is the stuff that Scott and I did on flared disks. You know, we did it a decade before Chang and Goldreich. And just to kind of boast a little bit, we actually calculated a self-consistent model, and asymptotically, it gives you the Chang and Goldreich solution for the temperature distribution. There's also a point that they made a big deal about the temperature inversion in disks. You know, that irradiated disks are hotter on top and colder on the midplane when the accretion rate isn't that high. They were unaware of Nuria's work, which showed that some years earlier. So let me just finish by talking about the obsession of why do T-Tauri stars accrete? And you can see I started out with why do they accrete? And then we wrote another paper how they accrete, because I couldn't say why again, why version 2. And I'm thinking about doing a third, but I can't figure out what the title would be. What? Well, there is a WTF possibility, but I don't think that would go. So we've heard about this idea that there's a magnetic disk wind, and certainly in the inner disk there's such a thing. That's the only way you can explain jets, and probably even some of the wider angle flow almost certainly has to be a magnetic wind. But then there's an issue of whether you have an outer disk wind that helps drive accretion. Photoevaporation certainly works, certainly gives you a flow. The question is how much magnetic field is there and how well is it actually coupled? Because if you don't couple it, you don't remove any angular momentum and you don't accrete. So I have to say that even though this may be right, I don't have a confident feeling about it. It makes me feel kind of uneasy. And because there's a huge amount of uncertainty about all the non-ideal MHD effects. And so then started thinking, well, do we really actually need to bring in stuff from 100 AU and bring it all the way in? Do we actually need to have this wind in order to accrete? And I think more and more about it when we see disks that have holes in them, and yet we can still get accretion, holes that may be drawn by planets and kind of damming up stuff. It'd be convenient not to have to bring it in across the gap and just have it be there. So, so a couple of years ago, Jaime and I think that got, well, the bottom line is we looked at low alphas. So if you have an alpha of nothing, then you can't have any viscous accretion. But it turns out that if you have an alpha of like 10 to the -4, you can just about put enough, right? So the problem is that if you have a small alpha in kind of a viscous idea, you can't accrete from far away because the viscous time's too long. So the smaller you make alpha, the closer in you have to accrete from. But that, and then you have problems because you don't want to make it too gravitationally unstable and you have too much stuff, okay? But you can sort of make this work to get TTR accretion rates for a few million years without having an alpha, if you can get an alpha of 10 to the -4, you could just do the accretion from the inner disk. And there's evidence, stuff by Mulders and Fred Chesla looking at taking disk mass reservoirs from the outer disk, where you can try and do it from dust and extrapolating inwards with a typical distribution. It's hard to get the masses of Kepler, et cetera, planets at small radii. So you can, maybe you just migrate, but maybe there's just more mass there in order to be able to do that. And that's something that actually happens with the FURI objects, because you can't have a burst of dozens of few Jupiter masses, 10 Jupiter masses in 100 years. You can't bring that in from 100 AU. You have to bring it in from short. So you have to have a big lump there anyway. And so the final thing I'm going to say is that we're also looking at what kind of outbursts you might be able to get, because stuff that like Phil Lucas is doing and others, there are more and more outbursts and they're small outbursts. And so we tried to estimate the conditions, and I can't really explain this now, but it's easier. You need less stuff to have an outburst if you can trigger it at small radii. And so then you should expect, and it actually turns out that the amount of stuff that you need to have small outbursts, for an FURI outburst, you have to have a huge bunch of stuff and have to be nearly gravitationally unstable. But you can get, if you can trigger it somehow, by triggering, I mean making it hot enough so that you ionize enough to get the magnetorotational instability to go, you can actually trigger it with stuff with kind of maybe a couple times the minimum mass solar nebula, and get bursts more like some of the things that are being seen with the Gaia outbursts. So I'm really excited to see what will come from the next generation of surveys as we look at some of these small outbursts, how frequent they are, and that I think will tell us something also about the amount of mass in inner disks as well. And so I think that's just going to open up a huge amount of stuff, and I'm very excited to see how that works out. Let me just then stop. I think you'll all appreciate that. And let me just stop on that slide. And so thank you.
Right. Well, I'm not going to follow that. I'm just going to say a couple of thank yous just to finish. Obviously, the first person I want to thank is Lee for all the wonderful work that he's done. And, you know, I haven't worked with Lee directly, but his work has certainly inspired me, like it has inspired others here. And thank you very much, Lee, for all of that. So, okay, just a few remaining thank yous before we all head off home. Last night we thanked the LOC because the LOC were there in person, so that seemed very appropriate. I'd like to, of course, thank the SOC for putting together, I think, an excellent program that's really reflected Lee's interest over the years, and I hope he agrees on that. The chairs for the different sessions, both the shall we say offline and online chairs that we used. I think my own feeling was that you know, a blended meeting seemed to have worked very well, even better than perhaps I'd hope it would have worked. And the last thing I want to do is thank the person who was behind the scenes all the time doing an awful lot of work, and she's probably still behind the scenes, hopefully there, Eileen. Eileen, can you come up, please? Not at all. It's easier. So thank you very much, Eileen. I think you've made certainly my life and the life of the LOC very, very easily. Thank you very much.
Thank you.
Okay, stay safe, as they say, and have a good trip home. Thank you.